every particular speaker had some issue or the other. There are different
We are
devices.
live, ma'am.
Yeah, no, please, yeah. Share the screen again, please.
No.
All the participants, please mute yourself. Please mute yourself. Thank you, all of you. Every particular speaker had some issue or the other. There are different devices.
We are live, ma'am.
No, please, yeah.
I don't know,
Share the
ma'am.
screen again,
My
please.
screen is automatically disabled.
All the participants, please mute yourself. Please mute yourself.
I think something
Dr.
is wrong.
Varsha, Dr. Varsha,
Something is wrong.
somebody's YouTube is coming in as an audio. So somebody's YouTube is coming as an audio. Whoever is flashing the YouTube, please switch it off. At least the audio part, I mean. Please share the screen. Are you able to do it? Yes or no?
Yes, ma'am. I've started. I
Yeah,
don't know,
again,
ma'am. Someone is just, or the network is there.
Okay, so what we do is, it's not a problem. What you do is, yeah. So I'm very much pleased to invite you all attendees, participants for this evening of learning physics with conceptual and problem-based approach. I'm very happy to welcome Dr. Savinder Kaur, who is presently working as an associate professor in the Department of Physics, SGTP Khalsa College, University of Delhi. She is an MSc and PhD from IIT Roorkee in the field of atomic and molecular collision physics, and has an experience of several years teaching undergraduate students in Khalsa College. And apart from that, she is a permanent member of ISAMP, Indian Society for Atomic and Molecular Physics, and does research in molecular physics, R matrix methods, and so on. She is very much concerned about the progress of the students and is known as a teacher who devotes a lot of time with the students personally and in group activities for their benefit. So I welcome Dr. Savinder Kaur, and I'm very pleased that you have agreed to give a lecture to our students and attendees and participants in this webinar series. Welcome, welcome again. I myself, along with Dr. Pushpa Bindal and my organizing team, are very happy to have you here. Kindly share your screen and start your lecture. Thank you so much.
Thank you for your kind words. And before I start my lecture, I'd like to take this opportunity to firstly thank the chairman, Professor Ajay Khattar, the secretary, Professor Anurag Sharma, you, the convener, Dr. Punita Verma, co-convener, Dr. Pushpa Bindal, and the organizing committee for holding such a wonderful event and working tirelessly to make it a success. So I thank you for this rare privilege that has been provided to me to deliver the series of lectures. I mean, I will be delivering 4 series of lectures on this platform, and this being my first, so I am sharing my screen. If it is visible, please let me know.
Yes, it is visible. Just make it a little bit bigger.
So the topics.
Please share again.
When what is gone, it's full screen on my desktop.
No, I think it's not shared. Just share again. So you have to share, then you have to choose either a window or a Chrome tab.
So
the way you did it just now. The way you did it just now.
Yeah, I just clicked on the window and I shared it.
Yeah, it has started. Yeah, it is, but it is closing again.
I think there is some problem with the Zoom today because the share screen is automatically disabled in a section of
the number of, okay, Miss Varsha, let's reduce the number of co-hosts and try again. So you have to be there. Remove me and Dr. Yogesh and Dr. Bindal once and see if it works.
Yeah, no.
Remove us from the co-host.
Dr. Savinder can send email to Varsha. She can send her PPT also.
Okay.
Yeah, but that will be a problem. How will I write on that?
No, sir, but problem is it is also happening with me when I shared my ma'am's introduction.
Okay, let's quickly reduce the number of co-hosts. Remove me from co-host, please.
Yes, yes, yes. You remove me,
Remove all of
ma'am.
us and test the sharing of the screen. Okay, Varsha?
Yes.
Ma'am, I don't know why I'm not getting that option. Okay, I got it now. Yeah. Okay.
Remove us from co-host.
Okay.
Keep only Dr. Savinder.
Okay, ma'am.
Dr. Savinder, it will take 1 or 2 minutes more. Please have
I have
patience.
I have no issues. I have no issues at all.
Okay, ma'am.
Uh,
Done. Yeah, done, ma'am.
No, I'm still the co-host. Remove me also. Yeah.
Done.
Okay, now you please try. Dr. Savinder, please try sharing your
yeah,
screen.
I am sharing my screen, and please let me know if it is visible.
Yes, it's visible.
That's good. So should I start?
Yeah, is this the slide from which you start? Then please just enlarge it a bit. Zoom, yeah,
I
yeah, yeah, yeah.
I I
Yes,
actually
yes, yes. Yes,
these are
perfect,
all
perfect.
PDFs.
Yeah, perfect, perfect, perfect. That's all. Yes, yes, yes. Perfect, perfect. Yes, that's it. And if
Okay.
anything else becomes a problem, then only stop your video. Okay? Only stop your camera. If
Okay.
network gives you a problem, then only stop your video. That's it.
Right, right.
Yeah,
And
please go
I
ahead.
stop my video from the stop video part, right?
Yes,
Just like you told me.
the symbol of the webcam, the camera
Yes,
symbol,
yes, yes.
only
I
that,
got it.
and
Yeah.
from your mobile, not
Yeah.
from your computer. Yeah, please start. Welcome.
Okay. Thank you so much. Thank you so much. So this being my first, and you can see all the errors I'm creating. So I start with complex analysis today, and the idea is to discuss the elements of complex analysis. And why I mean, I basically chose complex analysis here is because this study of complex variables is one of the richest areas of mathematical analysis. It has countless physical applications. And the idea of my lectures, as you can see from the topics over here, is just to establish basic concepts. And these basic concepts once developed should act as the building blocks for higher complex mathematics. So the first lecture, in fact, is for the introduction to complex numbers. And the second one will deal with the analytical functions and the elementary functions. So I will try to actually cover up 4 or 5 points from the second lecture also in the first one. Because of whatever timing problems we might have. So if I just start off here, this is the introduction to complex numbers, and I'll just increase the size here. I think that should be visible enough. So the idea is, first of all, what is a complex number and what is its origin? I take a pencil and it's equations like z squared plus n is equal to 0, and equations like a quadratic equation where a discriminant b squared minus 4ac becomes less than 0, that we did never got solutions of a real number. But I mean, going back into the history, we want to understand the origin of complex numbers. The earliest fleeting reference for negative numbers occurred in the work of a Greek mathematician that was Hieron of Alexandria in 1st century AD, and he considered the volume of an impossible frustum of a pyramid. So his most important work, geometric work, was Metrica, which was lost. Why I'm introducing all this to you is effectively because in the 16th century after that, the closed formula for roots of third and fourth degree polynomials were discovered. And when I talk of that, I talk of equations, let us say, of the type x cube plus 2x square minus x minus 2 equal to 0. So if anybody has a look on this kind of an equation, immediately that person knows that it has roots as real roots plus minus 1 and 2. However, if you go into the mathematics of this particular equation and try to solve it up, you will definitely encounter negative roots. Is there a problem? Hello? Okay. So maybe I will continue. And the symbol here is iota, which is a root of -1. And this is an imaginary number. And this imaginary word was actually used derogatorily and given by Descartes in the 17th century, because at that moment, basically negative numbers only were not understood. So square root of a negative number was, a very different concept. However, just let's go over to the representation of a complex number. The complex number is an ordered pair. Now, this is one definition that we are interested in. And the ordered pair is x comma y, keeping in mind that x in itself is a real number, y in itself is a real number, but it is called the real part of z and y is called the imaginary part of z. There is another representation that we have here, which is z is x plus iota y, but misconception mostly used by students. This plus is not an ordinary addition, it is just a symbol. So if I'm writing a complex number xy in the form of an ordered pair, I can also write xy as x0 plus 0y. And this 0y can be written as 01, which yields a representation to the iota as 01. And iota square becomes -10. Right. So the most important point that I would like here for the students to note is that x and y are always real numbers. Okay, so let's go ahead and talk of the sums and products of these numbers. If you have two real numbers, we very easily know two real numbers, add them up and you get the sum. Two real numbers, take a product, you get the product. It's the same case that you have in the real number, you have in the complex number system. The only difference in the complex number system is it is an extension of the real number system. So if I want to talk of two complex numbers and I want to understand that two complex numbers are equal, it just means that the x1 over here should match the x2 over here and the y1 over here should match the y2 over here. What does it actually mean? It means that it corresponds to the same point on the complex plane. It's the point that we are talking about. Similarly, the addition and subtraction of two complex numbers is going to involve the addition and the subtraction in the respective real parts of the x and the real part of the y. The multiplication, I presume everybody knows, we can write x1 plus iota y1 as the first number. We can write x2 plus iota y2 as the second number. We can multiply and get these products using the property of iota square as -1. The division is defined like this, where obviously the denominator x square plus y square should not go to 0. Is a graphical representation of complex numbers, which is very important because real numbers we present on a single line. All numbers, integers, rational numbers, irrational numbers, all of them we can represent here. But the idea of complex numbers is to add on a dimension. That means if I have a real number line, I can take another real number line, but the idea is different. The real number line that you take, just along with an x is actually that line which is perpendicular to the original line that you have chosen. That is the idea. So the complex numbers are points on a plane. This is the quality of complex numbers. And how do you plot them? You plot them like this. You choose two axes, x-axis, y-axis. This is a Cartesian format that I'm telling you right now. You make equal, divisions here, make equal divisions along the x and the y. Find out the coordinate for x, find out the coordinate for y, and this is the ordered pair that you are showing. But there is one more representation which is attached to a complex number. And that representation is that we are going to show this as a vector. This arrow that you see tries to show and tries to represent a complex number as a vector. And this representation is really very important. But this kind of representation at times creates a problem in the minds of some students, which I will clear when I talk of the multiplication. So this kind of diagram that we have up here is an Argand diagram, or it is called the Gaussian plane. And again, historically, why it is called an Argand diagram is because Argand was a accountant, a bookkeeper. He wrote a book on his own expense, and it was discovered. This kind of diagram was actually discovered later on and popularized by Gauss. But I think that people very little know about Caspar Wessel, who actually in 1799 was the first person to give the geometrical interpretation of complex numbers. It was easy to identify them as under root of minus iota, as under root of minus iota, and so on. But the real idea, the real geometrical interpretation of a complex number was given by Wessel when he mapped the map of Denmark as a surveyor. Okay, so maybe we will talk about it when we talk of some physical problems later on. So if we have two vectors, let us say I have a vector AB. Now, why am I calling vector? As I have told here that a complex number can be represented as a vector, and OP is the vector I'm talking about here, whose initial point is this origin and the terminal point is x comma y. So if I have two vectors, let us say AB is one vector, OP is another vector. These two vectors have the same length, they have the same direction, but the initial points that they have are different. Look at the points, starting points are different. So what do you see? You just see that they are parallel to each other, they are equal in dimensions, and the direction is the same. So two vectors of same length, same direction, but different initial points. This is how you plot them. Okay, what's the idea? The idea is that each point on the plane will exist only once and will correspond to only one complex number. And the distance between 2 points is given by this shortest line joining the 2 points formula, where we write mod of z1 minus z2 as under root of x1 minus x2 whole square plus y1 minus y2 whole square. So the addition of complex numbers. Now this is important because when you follow the addition of complex numbers, you follow it as an addition of two vectors. The law of parallelogram you follow here. You take Z1 as one complex number of vector. You take Z2 as another complex number of vector. And you just translate this vector over here, right? The tip and the head over here should match, and the resultant that you get is the sum of the two vectors z1 and z2, which is also the sum of the complex numbers. I'm sure most of you know this, but I am just going through this to have a preview as an introduction here. And again, when we talk of subtraction, we have z1 here or z2 here. Take a negative on this side as minus z2 and take a corresponding resultant of these two vectors by just first translating this over here as minus z2 and taking the resultant and getting the subtraction of the two vectors. Now, the misconception that I told you students usually have. If I call OP a vector, which represents, let us say, a complex number Z1, and let us say I call OQ as a representation for another vector Z2, then the product for Z1, Z2, I can represent by R, and I can call it as a new Z3 if you want. The idea that I want to make here is the students always think of OP as a vector, OQ as a vector, and when they think of them as vectors, they try to evaluate this fact that we have to perform a scalar product or we have to perform a vector product. So it should be clear that the product of two complex numbers is itself a complex number and it is going to lie on the same plane. So it's the angles which will get added, it is the magnitude which is going to get multiplied here, but the plane on which the Z3 will lie is going to be exactly the same plane as Z1 and Z2, and the scalar or the vector product has nothing to do with it. Okay, so we have some algebraic properties, and very well known in the real numbers case, same applied to complex numbers. We have the commutative laws, the associative, the distributive. We have the additive identity, the inverse, the multiplicative identity, the multiplicative inverse, and so on. So what is the multiplicative identity of a complex number? See, the idea of a multiplicative identity is always to carry itself back. So the number with the multiplicative identity should get the number back. So we just use this property here. Assume Z to be any complex number. Assume an identity form. And because you want to determine the identity form, you multiplied the number and the identity to get the number back. You equate the real and you equate the imaginary parts, rearrange them, equate and solve them. Finally, you get from this equation, which is an equation of a circle, you get y1 is 0 and x1 is 1. And the multiplicative identity is 1, 0. Now, again, sometimes some students have confusion here. Iota, if you remember, was expressed as 0, 1. Please remember this because you had an x-axis, and when we have an x-axis here, all the elements here were real. Similarly, when you had a y-axis over here, all the elements along the y-axis were also real. The only positioning here for iota is 0, 1, because we are representing it as an ordered pair. But the identity for a complex number is 1, 0. Again, what is the multiplicative inverse of a complex number? The number and the inverse should yield the identity. We all know that. So the number and an assumed inverse, which I don't know what it is, I need a form of it, should be equal to an identity. You multiply it again by the multiplicative rule, solve these equations by equating the real and the imaginary parts, get the corresponding x1 and the y1, and finally you end up with an expression for z inverse like this. You can get a z inverse subject to a condition that x square plus y square is not equal to 0. Now, a very small concept or a misconception as it is written here. We have product of two complex numbers, z1 and z2, and it is 0. Then we must understand that Z1 and Z2 will be 0, then at least one of the two numbers has to be 0. So let us start this understanding, and let us say that Z1 and Z2 is equal to 0. We can assume that one of the numbers, let us say Z1 is not equal to 0. And if Z1 is not equal to 0, we know that the inverse is going to exist. Why? Because if Z1 is not equal to 0, x1 square plus y1 square under root is going to exist. It's not going to be 0. Okay, fine. So we use this property. We write Z2. This is Z2 here. And this expression that you see here in the bracket is nothing but an identity. So Z2 is identity times Z2. And the identity we are writing in terms of Z1, Z1, Z1 inverse, and Z2. We just now read that commutative properties can be used. So I just commute it and then I associate it. So Z1 inverse, Z1, Z2, but Z1, Z2 is already 0. So this gives me what? It tells me that Z2 has to be 0. So what did I do here? I used the property of a multiplicative inverse, and I tried to show here that at least one of the two complex numbers must be 0. So this is the idea we make. Now, this question that I have here as an example here is really useful when you are applying it in different problems where you are talking of two non-collinear and two non-parallel vectors. So for example, let us read this question here. We have Z1 as x1, y1. Z2 is another complex number, x2, y2. And they are two non-collinear and non-parallel vectors. And if alpha and beta are real numbers, then they are such that alpha z1 and beta z2 is 0. You will have this condition met only and only if these two scalars, alpha and beta, separately go to 0. Now, why is it important? It's going to show you that you are talking of non-linearity. You're talking of non-parallel vectors. So the given equation here is alpha z1 plus beta z2 equal to 0. Fine. Replace your z1 as some x1 plus iota y1. Replace your z2 as some x2 plus iota y2. And equate separately the real and the imaginary parts to 0, because you have a 0 on the right hand side. This 0 means 0 comma 0, right? So we have real part here and we have the imaginary part here. You can write x1 alpha x1 as minus beta x2, alpha y1 as minus beta y2, and divide these two equations. And what you get here is this ratio. Y1 by x1 is y2 by x2. Now, what is y1 by x1? We all know these are the slopes of a line. So slopes of which lines? The vectors in question. So the slopes of the two vectors can be same only and only if they are parallel or collinear. So what did we get? We got only one understanding from here, that if we are writing this particular condition, then it is yielding me this unless my alpha and beta are 0. So we are given the condition that the two complex numbers are not parallel. This is what is the question, that the two complex numbers are not parallel. So when are they not going to be parallel? They will not be parallel only and only if the alpha and the beta separately go to 0. It's a very important property. You will need it in quantum mechanics. You will need it in many places where you're going to apply them. Now let us look up at the complex conjugate. The complex number z, again represented as x plus iota y, and z bar is the representation for a complex conjugate, x minus iota y. You add them up, you get the real component divided by 2 here, and you subtract the 2, divide by 2 iota, you get y. So the real part of z is the x and the imaginary part of the z is the y. Why is it important to understand a complex conjugate is we want to look up some symmetries at time. So arithmetic operations for complex conjugates are going to hold exactly the same way as they are going to hold for any complex number. So you have addition, subtraction, and you have the bars here. That means it's a product you are taking here. The bars of the fractions or the numerator and the denominator individually, they will behave as conjugates. We have all these operations holding. But the main idea of a complex conjugate is what? It is a reflection about an x-axis. This is an important concept, which has always something to do with symmetry. If you see, this is the z, and this is the z bar. And this angle is going to be exactly similar to this angle that we see. So they are effectively mirror images about the x-axis. So if a complex number is equal to its complex conjugate, what do we infer? The complex number is equal to the complex conjugate. That is x plus iota y is equal to x minus iota y. What do I get here? X should be equal to x, y should be equal to minus y. This cannot happen. This situation is not possible. So the only alternative is that x should be the only thing that should be existing, and therefore this complex number, which is equal to the complex conjugate, should be a real number. Now, if I have a sum of two complex numbers and a product of two complex numbers, and if both of these quantities are real, what do I say about these numbers? Okay, find out the sum. It says that the sum and the product is real. So obviously, this part is not there. And if this part is not there, I have two equations. Y1 plus y2 should be 0, and x1 y2 plus x2 y1, this should be 0. I solve it accordingly, and I get x1 is equal to x2. What is the idea? It's just the same idea which you had just now. If the real parts are equal and the imaginary parts have a negative sign amongst them, a relation that they are related, y1 is related negatively to y2, what are they? They are just complex conjugates of each other. So when you have two numbers which are real, I mean the sum and the product both are real, then the numbers are complex conjugates. Immediately it should strike you. Again, this properties are going to be useful later on to you all. Let's talk about the modulus of an absolute value. We have a non-negative real number, mod of z, as under root x square plus y square, and we write it as under root z z bar. Now, what does it mean? What are we trying to do here? We had a complex number here, starting from O to P, and the coordinates of this point P are x comma y. We would like to understand the length of this vector. So to understand the length of this vector, we calculate the modulus of z, which is under root x square plus y square, and we can write this as sum r. This becomes the graphical representation of the absolute value of z. So effectively, if you just see this formula, this is nothing but a distance from the origin, which I am calling the absolute value. So right now, the point in question is an origin. So it is a distance from the origin. I might like to change this point, and then I might like to understand what is the absolute value and what kind of region does it give me. There is again some small misconceptions that students have. You should never say that Z1 is less than Z2. It has no meaning. Because by Z1 and Z2, we only mean positions on the complex plane, where the point on the complex plane is located. However, if we say or make this statement that mod of Z1 is less than mod of Z2, then we are correct, because this is going to imply that the point Z1 is closer to whatever reference point. The reference point chosen by you right now is the origin. So Z1 is going to be closer to Z2 from the origin. So for an idea, you can take a point 1 plus 2 iota, take another point minus 3 plus iota, find out the modulus value. This is root 10, this is root 5. And the point 1 plus 2 iota has a smaller distance from the origin. So it's closer to the origin. This is the idea that we get. So never ever have this thing in your mind that we can say, okay, Z1 is less than Z2. No, we can only talk of the absolute value. Okay. So far we talked about distances from the origin. Now, what about distance between 2 points, z and z naught? So this is an equation we want to think about. What is it? Look at this graph here and try to understand it. Again, this is an x-axis. This is a corresponding y-axis. This is your complex plane or argand plane. The point z naught is the point of reference. And I am trying to do what? I am trying to locate all those points which are at a distance of r from this reference point, whether here or here or here or anywhere. So what do I get? I get that all these points lie on the circumference of the circle. So effectively, this equation is telling me that this corresponds to all the points lying on the circumference of the circle with the center as z naught. And obviously the distance, as you can see, we can calculate from the shortest distance formula. For example, here, if I have this question, find the locus of all the points with the center point at 1, 2 and equidistant from it by distance 3. So we know Z minus Z naught is equal to R. R here is given as, let us say, 3, and the reference point is Z naught. How do I go about it? I choose my Z naught. I take it as a center point, 1, comma 2. I choose the radii as 3, and I draw this circle. This circle is going to represent all these points Z minus Z naught equal to R. Now, how is it a circle? How do we verify it is a circle? So we just write here Z as X comma Y, write your Z naught, collect the real parts, collect the imaginary parts, take a modulus, and what you see here is an equation of a circle. So the locus is a set of points lying on the circumference of the circle, and the center point here was 1, comma 2. So the idea here is to introduce to you the curves and regions in a complex plane, because later on when we will go into the terse mathematics of solving integrals, it is important for us to understand where we are solving the integral and on what line are we solving it. So whatever line here means the contour that we choose, or the path that we choose, which is important. So we are more concerned with the set of complex numbers. So when we have this equality, we are talking of points which are lying on the circumference of the circle. And if you see this thing is shown in bold, there is no dot here. So equality means points lying on the surface of this circumference of this particular circle. So the curve is being drawn in bold. If I talk of this inequality, the points I'm talking about are lying inside, and they are not on the circumference of the circle. And therefore, this line has to be drawn dotted. It means the surface is open. It's not going to include the points on the circumference. Okay, now I come to the closed circular ring. If you see, there is an inequality here and an inequality here, but it shows something. There is an equality along with this inequality. What does it mean? It means that I'm talking of a region which is beyond R1, but which is inside R2. So beyond R1 is this region. Inside R2 is this region. So effectively, it is all this region in this annular domain that I have. And because of this equality, I am showing both these circumferences of circles with radii R1 and radii R2 as solid lines, because I have an equality over here. However, if I had got an open circular ring, I would have an inequality here like this. And I would be talking of, again, this annular domain, all this part here. But I would be showing these two lines dotted. For R1, it should be here. And for R2, it should be here. So the idea here is very clear. Where you are, in which region you are, whether you are keeping your region open or you're keeping your region closed. Are you taking the points which are lying on the surface into account or not taking them into account? That is important. Okay, so finally, a small conclusion we have here is that mod of Z, if it is less than R, if I have an inequality as less than, I will call it as an open set. If I have an equal to sign involved, I will call it as a closed set. And if I have both these cases up here, it's neither an open nor a closed set. So it is interesting to understand complex numbers if we talk of the polar form, and this is where most of the students have a confusion, and which we will try to clear and pick up, because we have right now learned here that x comma 0 is the point on the x-axis. We have 0 comma y is the coordinate on the y-axis for this, and the ordered pair is x comma y. Now look at this figure carefully and look at the way the angle has been represented here. you must see it is started from here, taking a circle here, and we are just trying to draw it like this. We could have just simply drawn it like this. So what's the idea of giving a curvature like this? The idea here is the distance from O to P, this R is constant. It's not going to change. This theta, the inclination of the complex number from the x-axis, that's also not going to change. This theta is also fixed. But this theta can be a theta when I start from x and reach here. It can also be a theta when I keep moving, and again I come back and reach here. I still reach the same point. I can go in a reverse order, go back like this and still come back here. I still talk of the same theta. So the idea is, what is an argument of Z? Now please note there's a small a written out here. The small argz gives me multiple representations of theta, because I can keep on rotating by 2 pi, by 4 pi, by 6 pi, whatever even rotations that I have of pi, I can do that, and I can still reach this complex number OP all the time. This vector representation I will always get. So what is the idea? The idea is to write the polar form. So we write the projection along the x-axis as r cos theta. We write the projection along y-axis as the r sine theta. You express z as x plus iota y, combine it, calculate the modulus value, the absolute value, and keep in mind your r can never be negative because you're talking of a magnitude. R equal to 0 has no meaning. So we always have an r. We have a point P here, and we have a vector representation to a point Z over here. But we are talking of this theta. And this theta, we want to call it argument, the small argz. However, we have to keep in mind that this argument of z denotes the angle measured in radians that the vector z makes with the positive x-axis. So it is always along this x-axis, and from the x-axis, the angle which we are talking about, which we are going to call small argz, the argument of z. Now it can be this theta, it can be a theta taken up like this, which is theta plus 2 pi, all possibilities are there. So it is any one of the infinite, you must understand this, it is any one of the infinite number of real values differing by integral multiples of 2 pi. Now there is a problem. We usually have an understanding of using tan theta as y by x, and we say, okay, we can just write theta as tan inverse y by x. But if we forget to specify the quadrant which contains the point, then the definition of that complex number, the placement of that complex number becomes wrong. Why? I would like to explain this here. Maybe I can draw it here. For example, this is the first quadrant, and we have the x-axis and we have the y-axis here. So if I have a point in this quadrant, I have no problem, because this theta and the slope here, delta y by delta x, will always correspond to this theta. However, if I have a line in the second quadrant here, why I'm saying line, I'm positioning my vector here. Let us say Z2 is the ordered pair or the complex number represented by this vector. And if I want to calculate the tan inverse of y by x, delta y by delta x, I will be talking of this angle, this angle. I'm not interested in this angle. When I want to give a representation to Z2, I am interested in the angle which this vector Z2 is going to make from this positive x-axis. Please remember, it's from the positive x-axis we talk of argument of z. So it is very important to specify the quadrant in which you are. A vector here, I need to talk of this angle. If I take a vector here, I need to talk of this angle in totality.
Sorry for interrupting you, ma'am.
Yeah. please.
Yeah, sorry for interrupting you, ma'am. There are few questions in the chat box. Would you like to take it right now or after the lecture?
I don't know where do I see, because I am used to the Gmeet and I usually see them and I answer them as I go by, but I really don't know what are the questions.
Ma'am, these are in the chat box. If you want, we can take them at the end. If you are comfortable now, we can discuss them simultaneously. I will read out the questions to you. There are actually two questions till now.
Yeah, please tell me.
Ma'am, one is from Dinesh Singh, that if R1 is equal to modulus of Z minus Z of A comma B equal to R2, is it equality?
I'll write it here. If R1 is
R1 is equal
can you
to,
repeat the question?
yeah, modulus of
Equal to
Z minus
Z minus
Z of A comma B, Z bracket,
Z of A
small
comma
bracket,
B means
yeah.
what? Basically, it's just the point, okay?
Yeah.
Where reference
Okay,
point, whatever you have, okay?
modulus stops, then equal to R2.
Yeah.
Is
Okay.
equality.
So it is an equality, but you must understand that you will have to apply the equality from both the sides. This, what is this? This modulus here is a circle. Z minus Z1, can it be equal to R1? Can I draw a circle with a radii R1? And can I draw a circle with a radii R2? I think, Mr. Dinesh, you should understand one thing. When we say A is equal to B is equal to C, it implies A is also equal to C. So if your R1 is equal to R2, this is a circle. And the equality definitely is there, because modulus Z, see, we just now did this thing. Okay, I think I should go back here to explain that. Okay, here. For example, what he wrote here is effectively sum R1, and he said this is equal to sum R2. So it's an equality. It means R1 is equal to R2. It just means that I have a circle here where the center is at naught, and the distance between these 2 points is always going to be a constant. Another thing that it says is that I have displaced my origin. You know, the origin was here, but the origin is now Z0. So in his case, it was A comma B. And what is the next question? The second question, please.
Yes, ma'am. It is also from Dinesh Singh that we know that x1 comma 0 multiply x2 comma 0 in bracket x2 comma 0 equal to bracket x1 x2 comma 0.
Okay, so
but iota square is minus 1 comma 0, which is ideally 0 comma 1 into 0 comma 1 product. So
iota is 0 comma 1.
Yeah, into 0 comma 1.
0
so
comma
how
1.
do we
Yeah.
get this? So there is some confusion to him.
Okay, I think I have a, okay, maybe I should take a snapshot of this, because I'll have to otherwise write it again. And maybe I can take a snapshot and I have a blank PDF, and I will rewrite it here and maybe make it a little smaller. It seems, okay, so this is the question.
Yes,
so the idea here is to, yeah. So Mr. Dinesh, try to figure it out. 0 comma 1, what is it? 0 comma 1 is this position. How do you represent? You write it as the x part, the real part, and okay, maybe I can write it as write it as 0 plus 1 times an iota, and
ma'am,
0 plus.
Ma'am, sorry to interrupt.
Yeah.
Maybe you can come
Yes.
smaller, closer to the mic, as the voice is very slow.
Yeah, I am holding this
Okay. Okay. Thank
Headphone.
you.
Yeah, yeah. I am holding it right in front of my mouth. I'm trying to do that. And see, I multiply this iota and I get a minus sign here. So I have to multiply this with this. I have to multiply this with this. And when I do this, it's a minus iota here. And I get a 0 here. And when I multiply here, I get a 0 and a 0, right? So finally, I get a minus sign because of the iota square as a minus 1. Is that clear? Is it clear, Mr. Dinesh? This you are multiplying with this. It's just like an x1 plus iota y1, okay? And you are multiplying it with an x2 plus iota y2. This is what you are doing. And just normal multiplication, iota y2 you multiply with iota y1. So iota square is minus 1. And iota x1 y2 you get. You collect the real parts, you collect the imaginary parts, and you get the corresponding result.
It is clear. He written.
Uh,
Yeah, ma'am, there is one small question from YouTube that please repeat the definition of ARGZ, argument Z.
yeah, I will do that because that is really very important. And I will go back there. And in fact, the definition is written here. Geometrically, the argument of z denotes the angle measured in radians that the vector z makes with the positive x-axis. So I'm going to use this opportunity. I think maybe I can change the color here to some other darker color, probably. Maybe I can choose a blue. So the idea here is that when we are talking of small argz, and we are representing a complex number like this from here to here is the distance that we have, the absolute modulus that we have been reporting. We're calling this as R, and this is the modulus of Z that we write. The angle that this vector makes from the positive x-axis, this is going to be the theta. And this theta will be the argument of Z. But what we have to be very careful about is that we can have Z here. So in that case, this is going to be the argument of Z. I can have different quadrants. I can have a vector here. This is then going to be the definition of argument of Z, keeping in mind this is the positive x-axis. Similarly, if I have this as the vector in the fourth quadrant, this is the definition of the argument of Z. Very important question here, because this is the basics of everything that you solve in integration also. So maybe I can go ahead now. Any more question, please?
No, ma'am. Thank you so much, ma'am.
Thank you so much. Okay, so the idea that I was trying to make here is that you need to specify the quadrant that you are taking here. And this small ARGZ has a very important significance because we are going to come over to a principal value also, which rather leads to more confusion than this argument of Z. So far it is very clear. We have chosen argument of Z and given it as a representation as theta. And the 2 and pi that you see again is this angle that I'm talking about. This is the theta or the argument of Z that I want to say. But if you understand, I can just take a full circle like this and still come back over here. So this is going to be just a theta plus 2 pi. It's an extra rotation of 2 pi that I write. So whether it is 2 pi, 4 pi, whatever it is, just doesn't matter whether I go clockwise or I go anti-clockwise. So if you can see here, this n is 0, plus minus 1, plus minus 2, and so on. So this is the representation that you have for a complex number. This is theta plus 2n pi, just plain and simple way of writing it. But now we come to an important concept. This is the important concept which actually hurts the students most of the time. The small ARGZ, I hope is clear now, but this is related to a capital ARGZ. Now, what is this capital ARGZ? This capital ARGZ is actually a choice that you are making, of a range that you are making, a sheet that you're making, or a branch that you're choosing, right? So if you make any particular choice in advance, please remember this, that the choice that you are going to make is going to be a choice that you make in advance. You are going to call it as a principal range, and that range you are getting, you are going to define it by argument of Z. Some places you will get the argument from minus pi to pi. Again, notice what it is written here. There's a capital theta written here, and there is an inequality written here, and there is an equality written here. It means including pi and not including minus pi. However, somebody would like to choose a range from 0 to 2 pi. No problem. You can include the 0. You can not include the 2 pi. Now, this idea totally confuses students. Why should I take from 0 to 2 pi? Why should I take from minus pi to pi? What I'm writing here is very clear. You can take any particular choice. Choice is yours. However, one side will be open and one side will be closed. Why? Because you are going to pass over from one sheet to another sheet. That is why you cannot include both the sides. This is one important thing to understand. A relation is very simple. This relation is the root of everything. The small ARGZ is related to the capital ARGZ by this formula. Somebody would say, I was just writing this as theta, and like here, I was just writing it as theta. So why can't you call this theta as the capital theta and write it as capital theta plus 2 and pi? Exactly, that's what I will do. So I can just simply write this argument of z as capital theta, this 2 and pi as it is, and write the form of the complex number as r cos theta plus iota sine theta. But please note that I am trying to write here the small argz, and the small argz has complete information about the position of the complex number, where it is sitting in this complex plane. So you can also use the Euler's formula and write it, because we know the Euler's formula is E iota theta is cos theta plus iota sine theta. It helps us to write easily. This small theta that you see in this whole presentation is always going to refer to small argz, and small argz is always going to be equal to capital theta plus 2 and pi. So the polar form representation, in short, I presume all the students should always keep it as R E iota small argz or iota capital argz plus 2 and pi. That is the idea, where your n can vary. Now the question is, why are we talking of this principal range? So I will try to pick up a question here and try to explain this. So if you have a problem here, you should point out. The complex number, let us see, is this 2 minus 2 iota. So what to do? First, locate where the point is. Draw your complex plane, the x-axis, the y-axis. Locate the 2 for the x and the minus 2. So you've got the point P here. Join it from the origin. Oh, that's that line. So join it from the origin to P. I should be drawing this. Okay, so this that you have joined here is the OP vector, which is indicating the vector corresponding to this complex number, and it is lying in the fourth quadrant. So if I want to find out the argument of z, I start moving from the positive x-axis towards this particular vector. I will have what? Pi by 2, another pi by 2, another pi by 2, and probably this angle, whatever it is. If I know that this angle is pi by 4, I know this angle is going to be pi by 2 minus pi by 4. We know all that. So that is the way of writing a polar form. So if you see here, this is the complex number that we have. You have located the points. You have located the magnitude by calculating the modulus. taking the under root of x square plus y square, and you want to write the argument of z along with a positive x-axis. But look at what I'm writing. I'm writing theta as minus pi by 4 plus this factor. But what did I calculate it as? Just now in front of you, I calculated it as pi by 2 from the first quadrant, another pi by 2 from the second quadrant, another pi by 2 from the third quadrant. And if I see this part, I think pi by 2 minus pi by 4 should be pi by 4 again. So it should be a pi by 4. So 1, 2, 3, 3 to the 6 plus 1, 7. So this should turn out to be 7 pi by 4. And what is the 7 pi by 4? This is small argz. How do I relate the small argz with the capital Argz? By the formula, which I know. I know this formula. Small argz is capital Argz plus 2n pi. Now use the value of the n. What n should I take? This is 7 pi by 4 is equal to capital Argz plus some 2n pi. Can I choose n equal to 0? I don't know. But the point is, what is the range of argument of z that I chose? Did I choose the range, principal range for argument of z from minus pi to pi, or did I choose it from 0 to pi? That is a question we have to understand. Okay. So what is the principal range that I'm going to choose for this argument of z? So maybe I can ask this question to the students here. If they can try and answer to me, what is the capital ARGZ? Will they be able to answer on the chat?
Yes, ma'am, they can write.
Yeah,
Students,
if they
please,
can, otherwise I will proceed.
students, please write your answers in the chat box.
Yeah, depending on the branch that you have chosen, I mean the principal range that you choose for argument of z. I wish I could see the chat box. I'm so used to seeing the chat box.
Ma'am, there is a reply 3 pi by 4 from Sejal Arora.
Okay, so let us see what it is.
And
Why
from
did I write a minus
Abhira.
pi by 4?
Yeah, okay. There are
Yeah, so
different answers.
writing, yes, they are different answers. And let us see, I mean, because this is exactly what is the confusion most of the time. We have a minus pi by 4 from somebody who wrote from the range minus pi to pi, and we have a 3 pi by 4. So let us just kind of see this. When you had a range from minus pi to pi, you could write a relation like this. Because minus pi by 4 plus 2 pi would give me a 7 pi by 4. If I had the specified range as this. However, if I had a range specified for argument of z from 0 to 2 pi, in this case, what would happen? Should I take it as 3 pi by 4? I don't think so. Look at it. Where was your point? Your point was somewhere here. And this is the small ARGZ. And if I choose my principal range from 0 to 2 pi, what should be the value here? 7 pi by 4 is less than 2 pi, and it is greater than 0. So in that particular range, the small ARGZ and the capital ARGZ happen to be same. So these are conceptual questions which, mostly the students make a mistake. So the best idea is always write your polar form, use this theta plus 2 and pi, just simply replace it by the small argz, which you know is the angle it's going to make from the positive x-axis. That's the best way of doing it and attempting a question. Okay, so when we understand that, we understand the equality of two non-zero complex numbers. I think I'm going very slow, so I'll just pick up some speed. We have two numbers here, so and we were talking of two numbers being equal, and especially complex numbers being equal. So maybe I can call this as a Z1, and maybe I can call this number as a Z2. And if I'm talking in polar representations, as long as R1 is equal to R2 and theta 1, which is small argz1, is related to the small argz2, then I have Z1 is equal to Z2. That means I'm talking of the same point. Now, what is the idea? Idea is the radii should be same. Obviously, the R should be same, but the theta can be this. The theta can be this. Okay. So I have all values of theta, multiple values, infinite values of theta available with me here, corresponding to this point, and this point is always going to be equal. The only thing I have to see is that this should be related. That means theta 1 and theta 2 should be related, where I am calling theta 1 as argument of Z1 and I'm calling theta 2 as argument of Z2. Okay, so the idea is that theta 1 and theta 2 should be related by a factor of 2 and pi. Then we have inequality of two numbers, complex numbers on a complex plane. Here's a parametric representation, most important in solving integral problems. This you see is just mod of z equal to r, because if we remember, mod of z means the distance of every point from the origin, and this distance is r, and I can just simply write this equation as mod of z equal to r. That's it. But how did I write z as r e iota theta? I am varying my theta. Please note these two equalities here from 0 to 2 pi, because I have to keep moving on this circle and I have to close this circle. And as my theta varies, this position keeps on varying as the theta is varying. That's what is happening. So I'm moving on the circumference of this circle. Yes.
Yeah, ma'am, there is a question from
Yes,
Abhiram
please.
Singh that please give the physical meaning of ARGZ, that is argument of Z, or it is just amplitude.
It has nothing to do with amplitude. If you're talking of, okay, so maybe if I want to talk of capital ARGZ or small ARGZ, I would like to talk of electromagnetism. We would like to talk of electric circuits. And when we are talking of electric circuits, we would like to talk of complex impedance of an antenna, and we would relate it to the let us say the electrical length of an antenna at that particular wavelength in use, and the impedance of an antenna, this can be matched to the feed line and the radio by adjusting the impedance of the feed line and using the feed line as an impedance transformer. So the complex form that you are having in this argument that you are talking to me about, it is going to help us in transmitting radio waves. It's going to tell us the phase that we are in, the phase difference that we have, and so on. And frankly speaking, if it weren't for this iota and all these arguments, we wouldn't be talking on the cell phones and giving these kind of presentations that we are giving here. And you will see all these arguments of Z's, coming up in different studies that you have. You will be studying them in fluid dynamics, in your quantum mechanics. So different interpretations you will get there. So the main importance is to, talk of the complex impedance. And as you are trying to say, the amplitude, you're trying to pick it up as amplitude, but I would like to say R is, the value that we're talking about, and theta is going to be the phase factor, something like you do in the waves, the optics, when you do diffraction. Okay, so that is where it's going to be an important concept picked up there.
Ma'am, one more
Okay, so
question is there from Sejal Aurora that can you please repeat why
okay.
we can't use the equality on both sides while defining a branch?
Yeah, I will come to that. Just give me some time, because there is a diagram I have made and I will probably show it there, everything.
Yeah,
And
sure, sure.
because you have to make a transition from one place to another, because I have 72 pages to go through in 3 hours and I'm right now only on the 26th page.
Sure, ma'am,
Okay.
sure.
So yes, I have taken up this point of the inequality that you are saying, and I'll come to this. What is the name of the student? I'll just write the name of the student,
Ma'am,
and I will
Sejal,
point it
Sejal.
out at Sejal. Okay, okay. I'll point it out to Sejal when I come over there. Okay, so I've written her name. Okay, so the parametric representation I'm talking about, basically, I'm not interested in this. I am always interested in shifting the origin and writing and giving a parametric representation, because the contour you choose can be anywhere in space, anywhere in the complex plane. So the idea is that I should be able to give this form of parametric representation. I should be able to write Z as Z0 plus R E iota theta. Vary your theta, your R changes, sign changes, and if you have theta is 0, you are here. If your theta is changing, you are here, you are here. So what did you do? You just shifted your origin by Z0, and this is the parametric representation that you are giving here. This one, the double arrowed one. So the point Z now travels in a counterclockwise direction, and it's going to trace out a circle. Maybe I can take the liberty of skipping De Moivre's formula, but I will just quickly in short tell you that Z1 can be represented, which you've already given a form. Please keep in mind this theta is the small argz. This theta 2 again is the small argz corresponding to Z2. So you're multiplying Z1 and Z2. So R1, R2 get multiplied, and cos theta 1 plus theta 2, sine theta 1 plus theta 2, all this comes from the trigonometric addition, subtractions, and the formulas that you do, the identities that you apply. So effectively, what did you do? You multiply two numbers, and these are getting added. You multiply n number of numbers, the arguments get added. Look at this. And if you are having the same complex number, all these z's are same, you can trace it to the power of n, and look at what happens here. All these thetas become same because their positions, their distances, angles, orientations from the positive x-axis, so they all become n theta. So r cos theta plus iota sin theta, which is the z to the power of n, is equal to r to the power n cos n theta plus iota sin n theta. And this is for all values of n which are integers. Similarly, we can write the multiplicative inverse, and this De Moivre's theorem can be used for now it has been proved you can use it for any form of n. Let us say p by q. I can take the 1 by q inside. If I have a p, I can take the p inside. When I say p by q, I actually say for n p by q. So the idea is, can this student somebody's trying to say something? Okay, so the multiplicative inverse can be written like this. I understand. Okay, so using the De Moivre's theorem, you can establish a few identities. Z to the power of n is r in cos n theta plus iota sine n theta. So what you can do is the left hand side you can open up and binomially expand. You can write it like this, as you can see here. And the binomial coefficients are related as NCR, like this. You equate the real and the imaginary part, and you establish the identities. So maybe I'd like to skip all this and come to the roots of complex numbers, because it's important to pick up topics like this, which are going to give an insight to the applications, that we have in different fields. Because somebody who's interested in understanding how argument of Z is understood, how an amplitude is understood, how we would like to use this. Okay, for example, how would I like to use the roots of complex numbers and use it in solving a differential equation? I mean, where's the idea applied and so on. So but first remember one thing, that when we do this, we are exploiting the definition of a complex number in a polar form. Okay, so Z is r cos theta plus 2k pi plus iota sine theta plus 2k pi. this can be small ARGZ, this can be capital ARGZ. Combined, if I write with capital ARGZ, this has to be small ARGZ. This has to be kept in your mind. So if you're considering omega as the nth root of Z, omega is any new complex number. So I can define it as some R and some phi. Fine. And if I go by this relation, omega to the power of n is equal to z, I can just write here omega to the power of n like this. And I can use the De Moivre's theorem and write it as r to the power n is cos n theta and phi plus iota sine n phi. And the complex number, which it is equal to the z, has this form that we have. So if I equate these two forms, what do I get? I get a relation. I get a relation which tells me that the new r for this corresponding omega will be 1 by nth time the r of the z in question. And the theta plus 2k pi, which is the representation of the non-zero complex number here, is going to be related like this. Okay, so the phi will be theta plus 2k pi by n. Now, again, I am forced to reduce the size of this because there is something which I want to show, together here. So forgive me for that. I want you to understand here that when you're writing a complex number, you can choose any value of k. Look at the k, it has been written, k is 0, plus minus 1, plus minus 2, and so on. So any value of k can be chosen when you're trying to specify the complex number on the complex plane, because you're specifying the position of the complex number on the complex plane. However, when I talk of an nth root of the same complex number, then this k cannot take all the values. And even if it does, it's going to be a repetition. I'm going to get the same thing back. So you must note this thing that is written here. The k is going to take the values from 0 to n minus 1. If I'm talking of n complex roots, I'm going to get n distinct roots. That is the idea. And if you go ahead, I mean, if somebody says, no, I would like to use n plus 1, and so on, what's going to happen? They are going to just get repeated. So these k values are just going to repeat themselves. So effectively, you will get omega as z 1 by n, which is r cos theta plus 2k pi and so on. And this is what you get. The main concept that you have to keep in mind is that k is going to take n values starting from 0 to n minus 1. And all these roots, they're going to lie somewhere. Where are they going to lie? They're going to lie on a radius, on a circle with the radius r1 by n. And they will be equally spaced by a factor of 2 pi by n. This is it. Okay, so let me just take a small example over here. Now look at this. This seems to be an equation. And you've been asked to geometrically locate the values of z for z to the power 5 plus 32 equal to 0. Now, what will you do? You just simply write z to the power 5 is minus 32. And this seems to be a very small diagram here, but it is trying to depict to you that, okay, this magnitude here is definitely 32, right? And because this is minus 32, I mean, this is mod 32, maybe I can write that. It's going to be a better way of writing it. So that's the magnitude that I have of this complex number, and the value is minus 32. But what complex number? The complex number omega, which I am going to write as z to the power 5, and which is minus 32. Okay, so it is this number which I am calling omega. I am writing it here. But I would like to get the values of z. That means I want to get 1 by 5 of this. So what do? I first try to identify this minus 32 in polar form. So I write this minus 32 in polar form. The argument of z should be what? It should be pi. It can be pi, it can be pi plus 2k pi, it can be pi minus 2k pi, and so on. So I have pi plus 2k pi and so on, all values for k. Everything allowed. Why? Because I'm still talking of the point, the polar form. Then I applied the De Moivre's theorem. I want to calculate 1/5 root of this. So maybe here I should have written here as, okay, maybe I should have called this as omega, but it's okay. This is exactly what I'm doing. I'm calling this as omega. So I am taking z as omega to the power of 1/5 here. So exactly that's what I'm doing here. So what you see is this minus sign has been incorporated in this pi. That is what you have to understand. And this 32 gives the magnitude, and 32 to the power of 1/5 is going to just end up giving me a 2. And what are the values? If I am taking 5 roots, I should have 5 values starting from 0 to 4. So Z is minus 32 1/5. The corresponding value for R is 1/5 of the magnitude over here. So that root is 2. And I have cos of the angle pi plus 2k pi by 5. I keep changing the values of k as 0, 1, 2, 3, and 4, and I get these values. And these are nothing but the placements of the roots that I should be getting, where I should be placing these roots. However, it is an advice to students, put k equal to 5, put it as 6, put it as -1, put it as -2. Any one of these values is going to get reproduced. So you'll just be moving on, the circumference of that particular circle and tracing out the vertices. And in this case, because it's a fifth root, it's going to be a pentagon. So you will be tracing out any one of the vertices of the pentagon. So what is it going to look like? Let us assume that this outer circle that I have drawn from here to here, and this is the point minus 32, which I was talking. And what you have done right now is taken the 1/5 root of this minus 32 number. How many roots you should get? You get 5 roots. So you get roots here which are lying on the vertices of a circle, of a regular pentagon here. I mean, 5 roots, so pentagon. And the angle, look at this. The Z1 is inclined at this angle. This is the inclination for the second one. This is the inclination for the third one, and so on. You have this. But all of them are basically lying on the circumference, or they are circumscribed on a circle which has a radius of 2. So please note this. Every z that has been written here, you are writing here an r and you're writing here a theta. So whenever you write a polar form, you write z as r theta. If you write a Cartesian form, you write xy. So because we are working in polar form and we are trying to find out the fifth root of a complex number, this is where we are using it. And maybe before I go, maybe I should do the nth roots of unity, because it's just parallel to it. If I take 1 and I want to take the nth root of 1, this is the position of 1. What's the argument of 1? 0, because it can be 0, it can be 2 pi, it can be 4 pi, it can be anything. But effectively, if I just take the first value, it is 0. So I can write 1 in this form, or I can write 1 in this polar form, and I can give different values to this k. So if I give different values to this k, I'm going to keep on rotating it by 2 pi, clockwise or anti-clockwise. But still, this vector, this OP vector, is always going to come back to its original position. So this is the representation that I have for 1 on the complex plane. But now what I want to do, I want to find the roots of this unity. So when I want to find the roots of this unity, I want to do this. I want to say z to the power n is 1, or I want to calculate z as 1 by n. Fine. I know what is z. Z is some r e iota theta. Okay. To the power of n, it is equal to 1. So let's use this. R e iota theta whole to the power of n. Again, apply the De Moivre's theorem. The left hand side will give you r to the power of n. And e iota theta is going to give you e iota theta times n. So that is e iota n times theta. So your n theta turns out to be 2k pi. This is what you get. your theta turns out to be 2k pi by n, and Rn is equal to 1. Now, what's happening here? You have this polar form, you get this representation from here, that Z is E iota 0 plus 2k pi by n. All these k values, because I'm talking again of the n roots, will take values 0, 1, 2, and so on, n minus 1. And we can represent any one particular value as omega. We call it as cos 2 pi by n plus iota sine 2 pi by n. This is exponential 2 pi iota by n. If you call this as the root of unity, the nth roots will be 1 omega omega square going up to omega n minus 1. So what are we saying? Geometrically, what are we trying to do all this for, and why we are trying to do all this? What are these roots representing? If I'm talking n roots, I'm talking of the n vertices of a regular polygon of n sides. Where is it going to be inscribed? It's going to be inscribed inside a circle with the center obviously as the origin here, and the radius over here as 1 because I've chosen unity. The circle will have a parametric equation mod of z equal to 1 or z is equal to re iota theta. We know that. And all these vertices, which are the roots, will be equally spaced by an angle of 2 pi by n. Okay, so what is the idea? For example, if I just simply ask you to, think, what is the second, third, fourth, sixth root of unity? So the idea comes from this figure here. If I am talking of two roots of unity, they are two roots diagrammatically opposite, situated on the circumference of the circle, which has a radius of 1. Similarly, if I'm talking of a third root of unity, so we have here the roots which are going to lie on the vertices of an equilateral triangle. It is 1 omega, omega square. And if I talk of the fourth roots of unity, you look at the figure, it's changing. I have here a square. And when I'm talking of these figures, you must understand I'm also trying to predict some kind of symmetry. And in physics, symmetry is most important thing which you're going to pick up in different subjects. This is a quadrilateral. When we talk of the fourth roots of unity, and the vertices here are the corners of the square. And look at this. This is your Z1. This is at an angle of pi by 2. This is at an angle of additional pi by 2. Another additional pi by 2, and so on. Similarly, the sixth root of unity will be the vertices of a regular hexagon. Okay, so the question is for the students, you can find the cube roots of minus 27 iota and try to show them diagrammatically. The cube roots, what should we expect? The cube roots should lie on the vertices of an equilateral triangle. And since we are talking of minus 27 iota, we should figure out where this minus 27 iota is, which should give us a presentation or a correct representation of small argz. Okay, so maybe I can work it out here. This is the position we have, minus 27. In the y, I'm writing it here. Why? Because this is x comma y. It was minus 27 iota, and this is the angle I'm interested in. If I choose my range of argument of z from minus pi to pi, then this capital ARGZ is going to come out to be minus pi by 2. And I can write the cube roots of minus 27 iota in this manner. I hope it is clear now. So roots will lie on the vertices of the equilateral triangle. The radius will be 3. And they will be equally spaced by this angle of 2 pi by 3. So how did I do that? I just took the number minus 27 iota. I wrote the polar form of this number, And the polar form of this number could be written as capital ARGZ plus 2k pi, because this happens to be the small ARGZ. This is again a form which we know. And I just applied the De Moivre's theorem. So brought the 1 by 3 inside. You have a minus pi by 6 and 2k pi by 3. Only thing you have to note here is when I wrote the number, I took all possible values of k. But when I took the root, I took only 3 possible values of k. This is the most important thing. Okay, so I think this should be clear here that the roots lie on the vertices of an equilateral triangle. They are equally spaced by an angle of 2 pi by 3. And obviously the principal root will be lying wherever this k is going to be 0. So the other approach, as I have told you earlier, is by identifying the exact quadrant. You can actually write the position by writing 3 pi by 2, which is going to be the small ARGZ. And again, whatever you find here will be exact replica of what you have found earlier. Okay, so I think maybe I'll just share with you a small application of this somewhere here. I had it. Okay, so here. So just now, what did you do? The nth roots of unity. And look at this. These are two examples and ideas of simple harmonic motion, vibrations of a beam. What are these? This is a second order differential equation. This happens to be a fourth order differential equation. So somebody can just get confused on how to solve it and so on. Nothing doing. It's a complex number. Just use it. You can just write it as z square plus omega naught square equal to 0, z4 plus k4 equal to 0. Translate them, find out the nth roots, use these values and get the real solutions. These are direct applications that you have when you are doing your physical problems. So maybe we'll come to this later on, but this was just to give you an idea and insight about the application of the nth roots of unity that you have. So maybe I'll just now take the liberty and start with functions here. Is there any question till this point here so that I can continue with the functions part?
No, ma'am. No question is there.
Dr. Savinda,
Okay.
would you like to take a break of 5 minutes or continue?
Maybe I'll continue unless there is something else required.
Yeah, no, nothing is else required. Nothing is required.
I will continue. Yeah, I'll continue. Yeah.
Please,
Because I
please.
have to finish by 8 o'clock, so I have just 1 hour and actually 2 chapters to teach still.
I'm
Thank you
enjoying.
so much.
It looks your lecture is like, it's like some sweet honey, pouring into the ears and teaching mathematics simultaneously. It's really very nice. Thank you so much. Very much. Thank you.
Thank you so much. Yeah, so I would like to talk about functions here. And when we talk of functions, there are a lot of confusions students have, which definitely have to be cleared. And it's going to be really interesting understanding functions. So the first idea here is that we want to consider a set S of complex numbers of Z. Okay, so this is the set of complex numbers. I apply a rule on the set and I get another complex number, which is omega. And this omega is the image that I'm talking of, right? So effectively, what did I say? I just said I applied a rule on Z. I will call this Z as a domain. And what I get as a result, I will call it a range. So F is going to map omega, F is going to map Z to omega. So your independent variable is Z and your dependent variable is omega. Now, before I go over to this idea of a domain and a range, because this is the main concept which is important, I will go back to this small figure I drew here to, first introduce to you the concept of a domain, a codomain, and a range, because this always creates confusion in the minds. For example, I take this set A and I have these 3 numbers, 1 to 3. I take another set B and I have numbers from 1 to 10. I apply a rule. I say X will go to 2X. Okay, so the rule is by this orange line. So this 1 goes to 2, this 2 goes to 4, and this 3 goes to 6. These numbers which are related by a rule will be the images. They will define the range. The numbers which are not related as well as the range is going to contribute to the codomain. So this is your domain, this is your codomain, and where you applied the rule, that is the range. So the idea is to figure out that what happens when we do this for functions. Okay, so I have a complex number omega as a result of a rule which has been applied on another complex number. So the f of z is f of x plus iota y, and I am getting uxy and vxy. What is this? These are some set of transformation equations. So what am I doing? I am going from a z plane and I am translating or shifting over by having applied a rule here. I am going over to a omega plane. Where am I? I am in a domain where I have specified a z, but look at the diagram here. It is showing to me that the domain is open. And the moment I apply a rule, I have fixed my range and I have closed that system. But via a set of transformation equations, because if I apply a rule, say I apply a rule as z square, which I will do just in my next next page here, I will show it to you that z square will have some relation here with u, because z square will be x square minus y square plus iota 2xy. So v will be 2xy and u will be x square minus y square. So what am I going to get here is that u on the omega plane is a function of both x and y. But where am I putting it? I'm putting it on one axis. On another axis, corresponding axis, I am putting a vxy. And I'm defining this as the omega plane as the image plane. So we have two planes to account for now. We have a z plane, which is the domain. We have an omega plane, which is the range. And we have a rule, which is the f. The polar coordinates can also be used here. So f of z can be written as f of r e iota theta. And the corresponding set of transformation equations will be in terms of r theta instead of x and y. So let us look at this, and it's going to be really interesting to see this, and maybe I can enlarge it. So if fz is z square and u is x square minus y square and v is 2xy, we have to see here that if u is x square minus y square, and let me choose a domain only in the first quadrant to understand what is the corresponding range for it. I do not know whether this is going to be visible, but I'll just enlarge it, but I am not able to shift it. Okay. It doesn't get shifted. So maybe I have to go back here. Okay. So let us see here what's happening, because I want you to understand the transformation equations. You are taking a region, a domain in the Z plane, and we are specifying X and Y to be positive because we are choosing the first quadrant here. The corresponding transformation equations for X and for Y here, u xy and v xy are x square minus y square and 2xy, right? Okay, so let's use them. Now, for x and y being positive, v is always going to be positive. However, for this u, we have to figure out, is your x greater than y? Is your x less than y? If your x is greater than y, u is positive. So u is positive, v is positive, we are in this first quadrant. However, if your x is less than y, u is negative and v is positive, we are in this second quadrant. So what did you see? A small region here, which was a small domain here, gets translated into a region, but look at the plane coverage. I mean, you had only one quadrant covered in the domain, but you have two quadrants covered in the range. Okay, so this is a very important aspect, and it's going to, be handy for you when we are going to discuss the Riemann surface. And as Sejal wanted to understand the branch transitions, and she said why we can't use an inequality, I'll be coming to that very soon. Okay, so similarly, just like you had the transformation equations in the Cartesian coordinates, you also have them in the polar coordinates. And if I go to the polar coordinates, And we see here, and I can pick up a pencil here also. You just see here that the function involved is omega equal to z square. And I'm just specifying a range for theta. And the range for theta I'm specifying is from 0 to pi. That means I'm specifying this whole range, this region. And what is it going to cover? For every theta corresponding to the z square, omega will be z square. That means r square e2 iota theta. That means the moment I move a theta in the omega plane, how much do I move? I move by 2 theta. If I have a dimension of r here, the dimension over here becomes r square. So look at the changes that are happening here. The most important thing you have to understand here is that this upper half z plane, including this real axis, which is your imaginary of z greater than 0, right, is mapped over to the entire omega plane, because the moment it becomes pi over here, it becomes 2 pi over here. So I've covered this whole region in the omega plane when I talked over domain existing from 0 to pi only. Okay, so let us go back here and understand few more things. Why it is important to understand these aspects are because maybe we study solid state physics, we study many applications of these complex numbers in many places. We might like to understand translation, dilation, reflection, rotation, all these symmetrical phenomena. So when we have something in a domain, let us take this circle here, for example, and we understand that this is 2, that means this is mod of z equal to 2, because we have understood how to write it. And if I say I'm translating this domain by 2, so what am I doing? I'm just shifting the origin by 2. This is the translation, and this becomes the range. I want to dilate it by a factor of 1 by 2. The radius becomes half. It is still the range. I want to rotate this vector by an angle of, let us say, alpha. I've rotated by an alpha. I'm here having a new range. So the idea is that geometrical characteristics of certain mappings are very important, like translation, rotation, reflection. Reflection means, as you have understood earlier, it's just the z bar. That means we can just talk of a conjugate and we have a reflection about the x-axis. So now this is an interesting thing, very interesting problem. And I like the students to try it, and maybe I can reduce the size so that they can see this. Now I'm just changing the domain and I still have the same function. Remember, I have just now only taken the domain where x and y were positive, but I now change the domain. I change the domain from minus infinity to infinity for both x and y. So the range of x square minus y square and 2xy, or effectively the transformation equations, will have a range in the entire UV plane now, right? But I can actually choose a family of curves here, and I can denote one family of curve as u naught and another family of curve as v naught, and I plot them. This is a plot I have made on Wolfram. So anybody can go online and plot it. Just give your expression as x square minus y square, you'll get this graph, and 2xy, you get this graph. Now the question is, I drew this family of curves. Why did I draw it? What is the idea behind it? What is the property between these two? How are these two linked? So what I've done here is, I've just cut a quadrant from this V naught curves, this family of curves. And what I try to do is I just try to, translate it over the U naught over here for you. Uh, where is it gone? Okay, so it just seems to have gone. Control Z. And bring it back here again. And that's it. I am losing it again and again. And the idea is to Okay, now I wanted to actually draw those lines, so maybe I can just try to figure them out like this and draw them here for you. And can you tell me what is the nature of these two curves now? Because what is more important for us is to understand the physical aspects. This was a domain. I extended the domain to minus infinity to infinity. The range is also the entire UV plane. I picked up the curves, and these curves are a family of curves, and I think I have an answer, orthogonal, and there's a question mark. Yes, they are orthogonal, but how do you prove them? Okay, so it's good one student has answered. The two families of curves are orthogonal to each other. And how do you do it? You just consider y to be a function of x, you differentiate them, and you find out the slope of the two curves, and you multiply the slope of the two curves, you will get a -1, which is going to imply that the two curves are orthogonal. Right. So these are some questions. I just took a function as its square. Maybe students can take a function as 1 by z and check if it is or these the family of curves are going to be orthogonal or not. They can also check it for a function as mod of z plus iota y minus x. In this case, they were not going to turn out to be orthogonal. So why is it important? You will understand. Because I would like to come to single and multiple valued functions. And basically, when we talk of multiple valued function, the input is associated with one or more outputs. Now, what does it mean? When I'm talking of a function, I'm actually applying a rule on z and I'm getting an omega. It means that the omega and the z have a relation, and this relation tells me whether the function is single valued or multiple valued. Okay, so usually we will be dealing with a single valued function, or if we are dealing with multiple valued functions, we will try to change them over and we will try to make them single valued functions. So we have a z plane, we have an omega plane, we have understood that. When we have one-to-one correspondence, then we say that the function is a single valued function, right? But what is a multiple valued function? The multiple valued function, for one value of z, I might have multiple values of omega, right? So two or more distinct values we have, and this range has more values here corresponding to the domain values that we had. What's an example? Example is very simple. We have an example as the square root of z. Say I had a 4 here. I would get here plus minus 2. If I had a 9 here, I would get plus minus 3. Now the question is, this multiple valued function that I have got, how do I make it or I separate it out into a single valued function? Because I have to do that to understand the derivatives and the functions, because if I am able to understand the functions, I am able to understand whether that function is analytical, then I can write all the higher order derivatives of that function. I can write all the derivatives, therefore I can write a power series. If I can write a power series, I can do, I can get information about everything about that particular function, and a huge amount of, a plethora of things actually open up in that particular case. So the idea is to do what? So what you can do, for example, I just said a square root. Take all the positive roots, put them on a sheet. Take all the negative roots, put them on another sheet. But there is a relation between z and omega by this rule f. So how do I connect those two sheets? So try to understand. I made one sheet and I said, put all the positive roots here. I made another sheet and I said, put all the negative roots here. How do I connect these two sheets? I have to connect them via something. And once I connect them, only then this rule can be applied. Okay, so a collection of single valued functions, each collection, this with plus the sheet is going to be called branch. this sheet, which is going to have all the negative roots, is going to be called a branch. So it's not effectively only for a function as z1 by 2. It can be for z1 by n, just now you read. If I take n roots, I will have n sheets corresponding to those n values, those n behaviors that I have. So we have to understand all these things, because you have just now found that if you took the n roots, let us say if you took 5 roots, you said they were lying on the vertices of a pentagon, 5 roots, pentagon. But I said there, if you remember, I took k as 0, 1, 2, 3, 4. The moment I said I take k equal to 5, you get one of these vertices back again. But actually, what are you doing? You are rotating by an angle of 2 pi and you are reaching another new sheet. So you will have different sheets. And if I'm talking of 5 roots, these 5 roots will probably lie on 5 different sheets. But I need to connect them. And I need to connect them via some line, some imaginary line, some arbitrary line. And I can call it as a branch line or something. Okay. So, and that branch line cannot be crossed over, because the moment I cross over that branch line, I will be moving from one sheet to another sheet. So that is the idea that I want to put across, because we will be dealing with multiple valued functions, but we will be converting them into single valued functions. So more to it, we will come to this. The idea that I want to make here is that the trigonometric, the hyperbolic, the exponential, the integer power functions, they are all examples of single valued functions. However, the moment you talk of log functions, they are multiple valued functions. All the inverse trigonometric functions are multiple valued functions. If you're talking of indefinite integral, it's going to be a multiple valued function. So how these things are going to happen, we will read. We will go ahead and understand that. But the only idea that I want to give to you right now is that the discontinuities of multiple valued functions in a complex plane are handled by this adoption of branch cuts or branch lines, any arbitrary line which we can draw and which we can cut, we can connect through the branch points. And when we have connected all the sheets together, we can call it as a Riemann surface. Okay, so it's going to come, and we will come to that. Slight ideas of limits, because we need to talk of limits, we need to talk of continuity, we need to talk of differentiable functions, we need to talk of analytic functions, and then we need to talk of the Riemann surfaces, or maybe we will talk of Riemann surfaces when we will talk of limits at infinity. Okay, so what are limits? Now, when I'm talking of limits, again, please keep in mind, I will be talking of a domain and I will always be talking of a range. And I'm talking of the domain in the Z plane and talking of a range in the omega plane. So what's happening here? If there exists a function f of z, which is defined at all points and is single valued, please note this word, and is single valued in the neighborhood of the point z equal to z naught, with the exception of the point z naught. Please note this, we are excluding this particular point z naught. Then we can say that this function fz will tend to a limiting value L as this z will approach z naught. In the domain where z minus z naught is less than delta, correspondingly, there is going to be a range fz minus L mod less than epsilon. So corresponding to every delta, there is going to be a epsilon. So a delta neighborhood in the domain and an epsilon neighborhood in the range. And what is happening? That the function f of z is tending to the limiting value L as z is approaching z naught in the domain. This is the idea of a limit, right? So the function is as close as desired to L for all the values of z close to z naught. But there is a very important concept in limits which is involved. The concept of limit is you can approach the limit from any direction in the complex plane, and the limit that you get has to be unique. And when we are dealing with multiple valued functions, the limit is going to depend on the particular branch that we take. Now, here's a short example here. We have a function as z bar by z, and we need to prove the limit does not exist. Okay, so I've just drawn these two diagrams here. And effectively, what we are going to do is we are going to prove by contradiction, because we are going to approach from different directions, and we are going to see whether we get the same limit. And if we don't get the same limit, obviously the limit is not unique, and therefore the limit does not exist. Okay, so we approach along the x-axis. Along the x-axis, y is 0. What is your function? Z bar by z. What is z bar? X plus iota y, x plus iota y. So y is 0 over here. Put your y as 0. Take the limit. You get a value as 1. Now approach along the y direction, along the y-axis. If you do that, your x is 0 along the y-axis. Again, put the values over here. You get a negative value. So what's telling you? It's just simply telling you that both our limits are not the same, and they are different, and therefore the limit for this particular function does not exist. Okay, so we have theorems on limits, and it's very easy to understand that if you have a function, u in itself is a real component, v in itself is a real component, and if we are writing omega as u naught plus iota v naught, u naught and v naught are real, though we are saying this is an imaginary part here because we are writing it in the form of a complex number. So you should approach u naught and v should approach v naught if your function f of z is approaching omega naught. This is your first theorem. So all theorems, like if you have a function approaching omega naught, if you have another function approaching capital omega naught, w naught, we can add, we can subtract, we can multiply, we can divide as long as omega naught is not equal to 0. So these theorems, I'm sure most of you know. But what is important for us to understand the limits of points involving infinity. So maybe I'll just increase this a bit because it's an important concept which we need to understand here now. Now this is interesting. So limits involving points at infinity. How do we do that? You know, students have an idea of doing all this in the real analysis. They simply say, okay, limit tending to infinity, replace your x by 1 by t, and if your x is tending to infinity, your t tends to 0, and so on. But what is the idea? What is the understanding? And what is a complex plane? You read a complex plane as one real axis x, another real axis y, inclined to it at 90 degree. But when we talk of limits which involve points at infinity, we need to talk of an extended complex plane. And when we talk of an extended complex plane, you have to understand, okay, let's take this sphere that you see, let us take it as Earth. And let us take this as the North Pole N, and this is the South Pole S. The North Pole indicates the point at infinity. So is corresponding to the point Z infinity. And the South Pole corresponds to the point which is the origin. But I need to understand why I'm using all this. I'm using all this because I need to understand where is this point of infinity on the complex plane. So to understand that, I need to extend my complex plane. And to extend that complex plane, I have to draw a Riemann sphere. And when I have to draw a Riemann sphere, every point on the Riemann sphere, I have to correlate, I have to correspond to a point which should lie on the extended complex plane. Okay, so what we do, you know, we just take this as a ball, take a needle, pierce it through from the North Pole, connecting whatever point which lies on this, let us say the ball, and, you know, extend that needle, and let us assume that this is a ball which is lying on a table. Your needle touches a point on the table. That point is the point on the complex plane, the extended complex plane that we are talking about. So what did I do? I took a line from the North Pole, connected to a point lying on the surface of the sphere, and I projected it outwards, and I got the point. on this surface, and this point is the point on the complex plane, and this projection that I have done is called a stereographic projection. So the point that we have to understand here is that for every point Z, there corresponds a point P on the surface of the sphere. And this sphere that we are having here is called a Riemann sphere. Okay, let's try to understand few more things over here. Now I have another figure here. Now, if you look, I know this is not really very clear, but I have taken this reference from the book of Foucault. And look at this, what's happening. I want to take this circle, which is on the sphere. And obviously, I'll again take a needle, I'll pierce it from the North Pole, connect with the points lying on the circumference of this circle, and try to connect it here. I'll get a corresponding image circle over here. And this image circle lies on the extended complex plane. So what did you see? The image of an arbitrary circle on the complex plane is also a circle that you're getting here. Now, it is just a spot here. What about a great circle, a longitude that I have? If I have a longitude and I start connecting the points from the North Pole to the point P, and then just connect it here, I will reach somewhere down this, I will reach somewhere on this line which I am extending, and I get a point somewhere here. Again, I connect from this North Pole, this point, and it comes to the straight line. Project it from here, okay, and it comes here. So what am I getting? I get a straight line on the complex plane, and it actually corresponds to this great circle, this longitudes. So you must try to understand how a longitude can be, projected stereographically on an extended complex plane, how a latitude will be extended. You can think of that, how a point, I've already told you, how a circle, again, a circle. So these are important concepts which come into play when you are actually going to do the real mathematics of Riemann spheres and surfaces. Yes, what we are used to is this. We are used to finding the limits at infinity of some functions, and we just simply use a transformation like this. We say z is 1 by omega. Oh, I'm so sorry, I just touched something. Okay. So we have z as 1 by omega, and as z tends to infinity, put your values and substitute for omega equal to 0 and get the limit. So there is no change in the mathematics, but the most important thing is the geometry, because it is the geometry and the symmetry which is going to help you to connect with the physical problems that we want to talk of later. Right. So let's go ahead and talk of continuity, because we have talked of limit. Now, when we talk of a continuous function, we want this function to be well defined at all points. We want this function to be single valued. And look at the definition that we are having here. We are having the definition that the limit of the function tends to the functional value at z naught. Now, note this thing, because when we wrote limit, we actually wrote a L over here. We did not write the functional value at z naught. So continuity has an additional requirement. It says that the limit must exist, and it also adds on to a concept that the functional value at that point should also exist separately, and both of them should be equal. And when they are equal, then the function is a continuous function. This is very important. Right. So maybe I'll skip all these things, and we know that if you're talking of continuity, we have some theorems. And two functions can be continuous if their sums, their differences, their products, their quotients are continuous also. Okay, so this is known, but the idea is that what one should keep in mind is that the continuous functions in every finite region are polynomials, exponentials, sine or cosine functions. So keep your point number one in your mind because you are going to use it. A continuous function of a continuous function is continuous. You're going to use that also. And another important aspect is that when your function is continuous in a closed region, it is going to be bounded. And when we say bounded, that means it is going to have an upper bound. And maybe somebody would have liked to point me out that I should put an equality over here and say that the mod of fz should be less than equal to some m. And if your function is continuous, the real and the imaginary parts of that function should also be continuous in that region. So what's the idea that I'm trying to put across? Look at the first point and this question I'm placing here for the first point. You have a function fz. You have here cosine, sine hyperbolic as a real part. You have an exponential. And you want to see whether this function is continuous on a complex plane or not. Uh, just, excuse me, I'll have to put my phone on charger. Just give me a second. So what do we see here is that the cosine and the sine hyperbolic are continuous functions, just as we found here. And the exponential is also a continuous function. So such a function is going to be continuous in the complex plane. Now, the most important thing that we are discussing right now is the derivatives of complex function here. Why? Because as I pointed out earlier, if a function has first derivative in some region, we can find all the derivatives of that function, they are going to exist. And if it is differentiable in a simple closed curve, then all the values throughout that region of that function can be determined. So the requirement for the derivative of a complex function is that it should be a single valued function. And I'm writing here f dash z naught as limit z to tending to z naught, fz minus fz naught upon z minus z naught. Now just think of the definition of the limits, and in that manner, try to recollect that what we are trying to say is as this value approaches this, when is it going to happen? It's going to happen in the range that we're topping. It's going to happen when your z approaches z naught. So you can also understand one very important thing is that the limits we learned that they are going to exist independent of the manner in which your z approaches z naught. So if you're talking of the derivative, approach from any direction like this, approach from your z, x, from y, from any curve that you take, but you reach one value, and this is a unique value that you are going to get. But the most important thing is you can find a derivative only of a single valued function, and hence the need of converting every multiple valued function into a single valued function. So I'm going to skip this because I'm looking at the watch and I just have half an hour and a lot of more concepts I want to speak. So maybe I will skip this. And I'll give you an idea of analytic functions, because a function is analytic at a point z naught if the function is differentiable in that neighborhood. And we have understood what a differentiability means. The limit should exist and should be equal to f dash z naught. Okay, and if the function will be analytic in a region, if it is analytical at every point in the region, that means if it is differentiable at every point in a region. Now, if I take a function as a conjugate here, z bar, you will find that by first principles, if you use it and you approach from different directions, the limit is not going to be unique and the derivative is not going to exist. There's another important theorem. I'll not go into the proof of this, but I want to only, though I've written it here, but due to shortage of time, I'm not going to take it up. The derivative of a function at a point implies continuity. This is important, but the reverse does not. So if I have a continuous function, okay, not drawn continuously because I have peaks here. Sorry for that. If I have a continuous function like this, it's going to have a derivative everywhere. But look at z bar itself. If I have a function like this is continuous but not differentiable. So derivative of a function at point implies continuity, and this is an important aspect we will keep in mind. And this is a small proof here. And the L hospital rule we can understand by again keeping in our mind that we have two function f and g, and if they are analytic in a region, differentiable at a region, differentiable at a point z naught and its neighborhood and its region. That is the idea of talking of an analytic function. And if those functions are 0 at z naught, but the derivative of the denominator that we are having, because if I have g prime, the g dash z naught not equal to 0, then the L hospital rule states that I can take the limit of z going to z naught and find it by calculating the derivatives of that and checking first whether I have finite values here or not. If I do not have finite values here, then I will again first check whether this function is analytic and this function is analytic, these two are analytic. And then again, I can take a second order derivative and apply the L hospital rule and go extend it further. So the idea here I'm trying to make is that if you have forms of 0 by 0, infinity by infinity, 0 into infinity, all these forms that are written here, they can be evaluated by appropriate modifications of the L hospital rule. And now come the most important things, which we have the Cauchy-Riemann conditions, the necessary and sufficient conditions for a function to be analytic. We wrote a function, that's the rule on Z, giving us a new complex number omega. And this omega we expressed as u and iota v, u and v with xy giving the transformation equations. But we have now a relation between the partial derivatives of u and a partial derivatives of v. So if the partial derivatives are continuous in the region that we are talking, and if del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x, we have the Cauchy-Riemann conditions. And correspondingly, we can define the derivative of the function using these Cauchy-Riemann equations as f dash z is del u by del x plus iota del v by del y. Right. So I have here z bar, which I know is not going to be an analytic function. Why? Because I know this is a conjugate and it's a symmetry. By symmetry, it's a reflection about the x-axis. It has, it is like something like this about the x-axis. So it's not going to be a differentiable function at a particular point, but I can just quickly check it up by using my Cauchy-Riemann equations. I check whether del u by del x is equal to del v by del y, which is not, and therefore this becomes a non-analytic function. But remember one thing, that once I have a non-analytic function, I will always have it as a non-analytic function, because these are checks for functions as exponentials of z or exponential of z bar and exponential of minus of z that I've done here. And you see that with z, it comes out to be analytic, but with z bar, it is going to come out to be a non-analytic function. Now, in addition to this, we have an important property that the Cauchy-Riemann conditions, when we talked of them, we talked of Cauchy-Riemann conditions to specify that a function is analytic or not. If it is analytic, we wrote a form of the derivative of that function. Now the idea is that if the two x and y exist, and if they are continuous in the region, then we can write, the second order. Look at this. This is del square u by del x square plus del square u by del y square equal to 0. And correspondingly, the same behavior we have with v. Now, what is this giving us? Why is it important for us to study and analyze harmonic functions? The idea is that this del square by del x square and del square by del y square that you have is actually an operator called del square, which is the Laplacian function. And these kind of functions which are going to satisfy del square, whatever I have here as u equal to 0. So these functions u that I have will be called harmonic functions. Now, what is the advantage of harmonic functions? The advantage of harmonic functions is if I know u, I can find the conjugate v. If I know v, I can find its conjugate u. Okay, so that is the idea. So the idea here is solved in a problem. Again, I will quickly brush through it. I have here u as y cube minus 3x square y. This is a function. And I check by calculating these values, I find that this u is harmonic in nature because del square u by del x square plus del square u by del y square is coming out to be 0. Now, obviously, if it is a harmonic function, u is a harmonic function, then a harmonic conjugate is going to exist. That means I can write the actual omega, the u plus iota v. I can always predict it. Now, how do I predict it? I predict by using the Cauchy-Riemann equations. What I am showing is it coming? I mean, I am trying to show something else, and I have something else on my mobile. Are we on the same platform? Hello?
Ma'am, we are seeing the PDF file.
Yeah, but can you see anything like uxy equal to y cube minus 3x square y?
Yeah, it is given in the solution first line, right?
Yeah, yeah.
Yeah,
Yes.
we
So
can see.
maybe I am, it's not probably coming on my mobile, so it's no problem. Thank you so
Yeah.
much.
Okay.
Okay, so we have the u as a harmonic function, and now what we do is we utilize the Cauchy-Riemann equations. And using these Cauchy-Riemann equations, del u by del x, we find out del v by del y. We don't know v, but we are able to predict v by using this expression of the Cauchy-Riemann equation. And we are able to, integrate it with respect to y, keeping x constant, and we are able to predict a v. But we don't know the phi, the function of x that we have got here. So how do we get that? We get it from our second Cauchy-Riemann equation, where del u by del y was minus del v of del x, and we had this. So what we do, we differentiate this equation C, get a phi dash x, and relate it here to equation B. Once we compare it, we are able to determine the form of phi x and hence the form of v, and hence we are able to specify the analytic form of this function, which is u plus iota v. Right. And we can find the derivative of this function as f dash z as del u by del x plus iota del v by del x. However, sometimes when we are attempting some questions, it is important for us to write in the form of the complex number z itself, which becomes a problem at times when you have different type of harmonic functions. So here's a shortcut to this. The shortcut is find out del u by del x, find out del u by del y. Try to write f dash z as del u by del x minus iota del u by del y. Once you have done that, that means once you have reached this position where I'm writing del u by del x here, I'm writing del u by del y here, put the y as 0, replace every x that you have by z, and you will get the derivative on the complex plane for that corresponding function. So you see here, I have got 3 iota z square after doing some calculation here, but I'll straight away get this. Now, how do I get this? This is what I'm telling you. You have you have checked it is a harmonic function. So you know the harmonic conjugate is going to exist. So you find out del u by del x, find out del u by del y, put y equal to 0, you get these expressions. Now you replace the x that you got by z and just write f prime z or the derivative of the function as u1 z comma 0 minus iota u2 z comma 0, and you have your answer as iota 3z square, and you can just match. It's the same thing. So your steps become small. This thing creates a confusion when you are solving for competitions as well as when you are solving for some important numerical analysis that you're doing. And this can be also done by understanding, put your y as 0 in the first relation here only where your function was analytic, and just simply replace your x by a z, take a derivative, and you'll reach here. So all options are available, all shortcuts are available. So Cauchy-Riemann conditions can be reached by doing partial derivatives. So I'll probably not go into them. This is the form of the Cauchy-Riemann equation that you get. The first del u by del x is equal to del v by del y. You do partial derivatives with respect to r and theta. You reach this. And then you do the second set of Cauchy-Riemann equations. You reach this polar form. Again, you use the Cartesian format of the derivative, and finally you reach this form of the derivative in the polar coordinates. And again, the Laplacian that we want to talk about, you can write here, this is going to be the Laplacian, you'll find it going to 0 in the polar coordinates. I'm skipping this because there's something very nice I want to tell you about the elementary functions, because I want to cover the question which Sejal brought up in the start. Okay, so now is the time to answer that. So I said in the starting that exponential functions are single valued functions. So see here, the exponential function I'm writing in the form of a power series. And please note in green, I'm writing the domain. This is an important aspect. Students must keep in mind the domain of your choice, because if your domain changes, your corresponding range changes. So keep that in mind always. This e to the power z is going to satisfy Cauchy-Riemann equation. It is going to be an analytic function. It is going to have all these properties which you see are available with real numbers also, but it has one specific property not shared by the e to the power x kind of a number. What is that? And then that is what is important. You write e to the power z plus 2 pi iota. I can write it as e to the power z, and I can write it as exponential 2 pi iota. What you see in the figure is that, look at this. If I had exponential to the power of x, where x was a real number, the e to the power x is never negative. While if I'm plotting here e to the power z in this figure, you can see that e to the power z has got values which are negative. But please remember, e to the power z or exponential functions are single valued functions. Okay, so I am just moving over on a surface and I'm getting these values. This is for the real representation, and this happens to be for the complex representation that I have. Now, the question is, how can e to the power z be written as a negative number? Look at this. I just now told you exponential of a real number never takes a negative value. For positive x, for negative x, y is always above. It's in the first and the second quadrant. It's not coming here. This green line is not coming down below here. So what is the idea of saying that e to the power z is -1? The idea here is to understand that we will be able to write the argument of this -1 here as pi. We will be able to write it as exponential iota pi plus 2k pi, write it as -1, equate the real and the imaginary parts, and we will be able to find that this z, which we write as x plus iota y, corresponding to this equation, your x is going to come out to be 0, is just a periodic function with a period of 2k pi. 2k plus 1 pi I. Keep your k as 0. You have pi I. Then you keep it as 1. You have an additional 2 pi. entering up. So this is what is happening. Additional 2 pi keeps entering up here in the e to the power z. Now comes the property of logarithmic functions. When you write log functions, it is the arguments which are very important. And the small argz was related to the capital argz. This is what we did, and I emphasized on this relation because I wanted to talk of log functions. And we can have a log function written in this form. We can have a log function written in this form where omega is log z or e to the power omega is z. If I write omega as log of z, and I can use this definition here, but how do I reach this definition is an understanding which we need to know. E to the power omega is z, omega is u plus iota v, and z is r e iota theta. This is the polar form that we have. And omega as u plus iota v, I use the property of the exponential and just open it up. So I'm going to compare the real with the real and the imaginary with the imaginary. I get u as log r and I get v as small argz, which is the theta. I'm able to write omega as u plus iota v, which is log of r plus iota theta. Now, r is modulus of z and theta is argument of z. Please note, you can use any principal range that you want. You are able to write omega as log of z as log of mod z plus iota capital argz plus 2n pi. If you specify the quadrant, you can use its definition of tan inverse also. But what is important here, which is the main point that I want to make here, is this n sitting up here, which is going to give you infinite number of values, telling you that log function is going to be a multiple valued function. The moment I put my n equal to 0, I will be talking of a principal branch, and I can call this small lnz as capital lnz corresponding to the principal branch in question. However, I would like you to note one thing which is written here. Log of 1 means log of mod of 1, which is 0, plus iota theta. If I am drawing 1, I am here. So this theta is 0. What do I have? 2n pi iota. This is log 1 value. If I have log of minus 1, I am here. This is minus 1. And the angle that I'm making here is pi. So I will always have a pi plus 2n pi here. So therefore 2n plus 1 iota pi as a definition for log of minus 1. So this is what I want to put across here. What is log of 0? Infinity. So when I say log of 0 and I say at 0, am I correct if I'm saying log of 0 is infinity? Anybody would like to say here, or minus infinity? Anybody would like to point out? No answer. Is it? Okay.
No,
So maybe
nothing
I'll
is
just.
there.
Okay. So maybe I would like to say that I'm writing here log of z as capital ln z plus minus 2n pi iota, and look at this figure out here. And if I try to show you, this is a 0 coming up here and this is a 0 coming up here. And if I match these two, this is a line that I'm not able to draw this line here. This line, this vertical line that you see here is actually a line which is a branch cut. So if I am on one sheet, I am going to traverse on this purple one. If I'm going to move over from this sheet to another sheet, I'm going to make a transition from this line. And this is where I answer Sejal by telling that if I want to stick on one sheet, I cannot include the transition point. The transition point is going to go over to the next sheet. And this transition point is taken into account by only the argument of Z. This argument, this theta takes into account this thing. So the transition that we have from one sheet to another is taken into account by the argument of Z. Another important concept is that exponential of log of z is equal to z. This is always true, but the reverse is not true. That means log of exponential of z is not true. Why? Because exponential of log z is always going to yield to me a z. It's going to happen. But the moment I talk of log of exponential of z, because of this argument of e to the power z and this extra 2 and pi values, I will have multiple values and I will never be able to get omega as the z back. So the idea that I am trying to make is, because the log function is a multiple valued function, log of e to the power z is not equal to z. It is z plus 2 n pi iota. That's always going to happen. However, if I'm taking an exponential of a log z, it is going to come out to be z. This you have to be careful when you are calculating your residues and your integrals in some physical problems. And all this that I am saying, this transition from one cheat to another and so on, is all based on this logic. And the logic is that log of z1, z2, the product, of the two complex numbers that I'm taking can be expressed as a sum if this, I am talking for small argz. But if I'm talking of the principal value, this equality is not going to hold. Why? Small argz1 is written like this, with capital theta 1 plus 2 n1 pi, and small argz2 is written as capital theta 2 plus 2 n2 pi. I can write argz1 z2 as a sum of these two numbers, which are your capital ARGZs, and this n1 n2 can be related in a fashion to give me the n that I have. So this condition is going to be met always. However, if I write the same condition with capital ARGZ, we will not get it. That means I'm writing log of Z1 as log of mod of Z1 plus iota capital ARGZ1 plus 2n1 pi. Similarly, I'm writing for log of Z2. I'm summing them up because I'm trying to get the product here. I will get this log of Z1 plus log of Z2. I will also get the sum here. And I will be able to replace this n by some combination of n1 and n2. And I will be able to prove the equality for two complex numbers Z1 and Z2. Right? So, but it does not happen here that log of Z1 and Z2 is not equal to log of Z1 plus log of Z2. Why? Because I cannot do it with the capital ARGZ, and this is an important concept. I just want to tell this. Will I be getting 5-10 minutes extra because we started late and it's almost 5 minutes to 8:30?
Yes, ma'am. Yeah, sure.
Okay, so then I will not actually try to speed up. Thank you. So I want to make this, thank you so much. I want to pick up this point here because this is confusion always arises because of the choice of the principal branch as well as the understanding of capital ARGZ. So I've taken a very simple example over here. I said Z1 is -1, I said Z2 is -1, and I'm talking of product of these two complex numbers is 1. So I represent Z1, which is -1, by this arrow here. This is a vector representation I give. I talk of this argument of Z1, and I say this argument of Z1 is pi. Similarly, argument of Z2 is pi. Now I plot the product Z1, Z2, which is 1 here. This is the arrow that you see. And the argument of Z1, Z2 is 2 pi. It can be 0, it can be 2 pi, it can be 4 pi, it can be 6 pi, it can be any one of them. So if I pick up any one value of that one, which I want from the argument of Z1 plus the argument of Z2, I can pick it up. That's the idea I'm trying to make here. So if pi plus pi, I can have a 2 pi here, I will pick it up because I know that this equality is going to get satisfied by that picking up this value of 2 pi. However, principal branch we have to fix because we are going to fix for the capital ARGZ. Now again, go back to this and try to understand. the capital ARGZ in the range 0 to 2 pi is pi. And in the range, now let me write it as, let us say I took the other range as minus pi to pi. And this is your ARGZ. Okay. So I'll talk of both the ranges so that it is absolutely transparent what I am speaking here. The capital ARGZ1 for both the ranges is pi, because pi is included here. Pi is also included here. It's here. It is here. Now come here. When I have the product of these two complex numbers, I'm writing 1, comma 0. So the capital ARGZ here is 0. Why? Look at this range. 0 is included here. 2 pi is not included. So what will I pick? I will pick 0. Again, look at this range. I can pick up 0. Why are we picking up these principal branches and principal ranges? Because we have always to pick up a range of 2 pi with one point inclusive and the other point not inclusive. So it just does not follow from the capital ARGZ, and therefore this relation of ln, the principal values, if I'm calculating, is not going to hold whether I am taking a product here or I am later on taking a division here. It is not going to follow. Then if I take talk of complex exponents, we have omega z to the power alpha, which can be written as E alpha log z. And again, the property of log z can be utilized. And understanding the arguments of Z, we can, just get results over here. So I think this is just mathematical calculation, and I would like to skip it here, because what I'm trying to do here is omega is Z to the power alpha, and I'm writing E as alpha log Z. Please keep in mind, you don't touch the alpha, you just change the log Z, and try to write it with the definition that you know of the log parameter now as log of mod z plus iota argument of z. You know how to write that, you know how to write the arguments, put the values, do your calculations, and you'll be able to reach these values. Similarly, you will be able to calculate the principal value of iota to the power of iota like this. Because what you need to do is just write it as iota log iota, and write log iota as log of mod iota, iota argument iota, and the argument of iota very clearly we can see is pi by 2, and we can use it. Put your value k as 0, you get the principal value, which is this. Same property of log can be utilized if you have complex bases. For example, if I want to just calculate log AZ, I will just take an example here. Log 10Z, I can just write it, change the basis as log Z by log 10, write log Z, define it as log mod of Z plus iota argument of Z, solve it, you can do that. Now comes the main thing. We talk of trigonometric functions. Remember one thing, the geometrical definition of a side and a hypotenuse, this definition that you always have of sine theta changes when you are talking of complex numbers. Corresponding to this domain, I'm writing sine z. Corresponding to this domain, I'm writing cos z. And this is the expression that we get for e to the power iota z by using the Euler's formula. Now, I can use all these identities and get the trigonometric identities. These are established, and one can always work them out. I only want to emphasize on the periodic character of sine z and cos z, because sine z plus 2 pi is sine z, and the same thing happens with cos. But the moment I have a pi increment, there's a change of sign. And it is this modulus of sine z square, which you are seeing these relations out here. These relations are going to be important because they are going to show to us that sine z and cos z are not bounded in absolute value, though sin x and cos x are bounded, right? And why I'm talking of bounded and non-boundedness is if you have functions like tan, secant, cot, and cosec, it's this cos z, this sin z. Is it becoming 0 anywhere? if it is becoming zero anywhere, then this function becomes, infinite. It blows up. It becomes non-analytic. So it is not bound to the system. And then I need to calculate the residue, the contribution towards whatever integral that I have. So basic thing is I need to understand the zeros of a function. And the zeros of a function will be whatever point where the functional value goes to 0. So I want to talk about the zeros of the sine function. And sine of z, if you open it up like this, comes out to be sine x cos hyperbolic y plus iota cos x sine hyperbolic y. Now, this is what I want to emphasize here, that this is the real component. This is also the real component. This is your u and this is your v. The u and the v should simultaneously go to 0. Only then we are able to define the 0 of sine z. So what do we need here? We need that x and y should be real, and obviously cos hyperbolic y is going to be greater than 0. So the first condition we have is sin x should be 0, which will be satisfied for these corresponding values of x. But these values of x simultaneously will not make cos x to be 0. So what are we left with is sin hyperbolic y going to 0. Okay, so these are some contour plots, and I really want to discuss them because I want you to keep in mind the sin x is going to 0 in this blue part, which is the u part, and in the green part, which is the v part. Corresponding to the sin x, the cos x cannot go to 0. So we are having two very important conditions here, which are these. This is the condition that we have here. Okay, so the condition is that x should take up these values and y should take up these values. Now, these are some contour plots. You must understand that when we plot sine x on, and we've got an idea, we always plot sine x like this. We have this, and where do we plot it? We plot it on an xy plane, but a complex number is already on an xy plane. So where do we plot a sine z? We plot a sine z in 3 dimensions. We've got to think about it in 3 dimensions. So what you see here in the contour plot is a dimension x, a dimension y, and a dimension by colors. So if I denote here the darkest color with the maximum minus, why I'm saying minus? Because in the real, you call this minus and you got this plus value. So just thinking that what is the behavior of sin x in the real space, I'm going to the complex space here. This is the larger negative value. This is also a negative value, a slightly lesser than that. And then I'll have a slightly lesser and a lesser and a lesser and a lesser like that. And then this becomes larger here again and some value here. So what you see is only a negative value of sine z being represented here. The corresponding plot that you see here has a high positive plot. A high positive plot, but a little less positive than this one. Again, okay, so this became a little bigger. Sorry for that. So this is again a positive, but slightly lesser positive than this, and so on. This thing happens, and again you have a big, larger positive here, a lesser positive here, and a positive here, and so on. So what you have to understand is a transition from a positive to a negative will take place only at a boundary where it's going to go to 0. And look at this. Where is it going to go to 0? Here. It goes to 0 here. Along this line that you see. It goes to 0 here along this line. It goes to 0 here along this line. And what are these zeros? These zeros are 0 plus minus pi, plus minus 2 pi, plus minus 3 pi. And this is what you got. So for the real part of sine z, this is the expression you're getting. Now let us look at the imaginary part of sine z, which was cos x sine hyperbolic y equal to 0. Now here there's a different story. You see that the positive part here, the negative part here has a positive counterpart here. That means I have a larger negative, I have a larger positive, just opposite it. I have a slightly, smaller negative, and then a smaller negative, and then all these negatives here. And again, smaller positives and positives like this. You have a boundary here, this interface. This is y equal to 0. The same thing happens here. You see this interface. then this interface and this interface. So all these interfaces that you see here are telling me that y is equal to 0 is the condition. So when I'm talking of simultaneously, these two conditions matching, what am I talking of? I'm talking of conditions on these lines matching, and I'm talking of conditions matching on this line. So if I introduce this line over here, where are the zeros of sine z? The zeros of sine z are here, here, and here. But in the third dimension, somewhere up. Okay, sorry for that. Okay, so I think it's visible now. And the same thing, I think this is an interesting thing, and these contour plots are very important later on when we study hard physics. Same thing happens with the hyperbolic functions, the sine hyperbolic and the cos hyperbolic, and there are some relations here which everybody can figure out. And this is a question I would like to put to students. They can try to figure out the contour maps for cos hyperbolic z going to 0 and sine hyperbolic z going to 0. The idea that I want to put across is that when you talked of sine and cos, maybe I can go back to this. When we talked of sine and cos, we were talking of x and y. Look at these values were along x where we are getting the zeros. And when we are talking of cos hyperbolic and sine hyperbolic, we will be talking on the iota, the arbitrary axis, which is the y-axis. The zeros will be lying somewhere there. Similarly, the zeros will be lying somewhere on the iota axis. So this is something which students can practice. Again, this property students can use. Now comes the inverse of trigonometric functions, and omega is cos inverse z. I realize that there are some questions which I have to answer, so I'll just take them up after another one or two. I think maybe this is the last page or second last. So I'm taking here an inverse trigonometric and a function here, omega as cos inverse z. I'm trying to give you an idea here that when you write cos omega in the form of the exponentials, you end up with the quadratic equation. When you find the roots, you take, you find the root, you get e iota omega as this, and when you take the log, this log introduces multiple values. And the moment you take a log, infinite values have been introduced. So your in trigonometric functions, which were single valued, their inverse becomes multiple valued. So maybe I can take up questions if people want, because I just wanted to put it across here that the inverse functions will always involve Riemann surfaces like this, where you will have to transit from one sheet to another. And each sheet will be a branch in which you will have only one possible rule being applied. Though the rule is same, and maybe a particular property of a rule which isolates it as a different set. That is the idea that we will try to make. So maybe I will not go through this summary. Maybe just some works which students might like to read and some suggested readings. So yeah, questions, please.
Thank you, ma'am. Just I want to make an announcement that I have posted the attendance link.
Yeah.
So please fill within 10 minutes, as after that the link will be closed. Ma'am, there is one question from Gayatri, that what does an open domain mean?
You see, the open domain here means I have a region here, and open domain means an open set. An open set means you do not include for example, I hope I am able to draw it properly with whatever possible things I can do. Maybe I am just trying to draw it arbitrary like this. This dotted framework that I have drawn, is basically that I am not going to include the points lying on the boundary. So when we usually, it is an idea of defining sets as open or closed, while the closed set is going to include the boundary points. So when I say domain, I mean an open set. Any other question?
Just ma'am, you asked for the log 0, so there are some answers that it is indefinite or can be positive or negative infinity, both not
Y-
defined like this.
yeah, that is important. And there is another question. I wish
Yeah.
I could see the messages. I mean,
Just one, yeah,
sorry.
just a rhyme from Sejal that miss, what is the need to introduce two branches at all? Why not work with a standard branch from 0 to 2 pi?
You can work from 0 to 2 pi, but you call the branch 0 to 2 pi as the principal branch. But Sejal, if I have a set here and I have another set here, and this is your Z and this is your corresponding omega, and if I just I mean, I just simply let's take it. I mean, let me just take an example for you, and say that the rule that I am applying here. I'm sorry for the handwriting. The rule that I'm applying here is z to the power of half. That means if I have 4 here, okay, so omega is going to have correspondingly 2 values. Now, what is the meaning of this? The meaning of this is that if I have z as r e iota theta in the domain in question, and I want to find out omega, which is z half, I can apply the De Moivre's theorem. I will write r half over here. Please remember this theta is the small argz, which is capital theta plus 2k pi, multiple values I can take off the z. So this z is any point on this x and y, which is the z plane that I'm talking about. And this z is everywhere, okay? So I am drawing it in the first quadrant, but please try to understand it can be anywhere in the quadrant with any theta, and this theta can keep on varying with the factor of 2 pi, and this is what I am on a set plane. I go over to a omega plane now. Now look very carefully. When I go over to an omega plane, this is the definition I'm giving to an omega. I will have omega 1, okay, as, let us call it R1. So R1 is going to be the same thing, but I'm just for your understanding, I'm writing is R1. I will have exponential iota theta 1 by 2 over here. Okay. Now, what is the idea that I'm trying to make here? The idea that I'm trying to make here is you keep on rotating here by theta, you rotate here by half an angle. So your omega 1 will probably in the omega branch here will be some smaller magnitude, obviously, because it is R1 to the power half. And the angle will also be somewhere half. And this is the root value that you get. Okay. Now try to understand. This is omega 1. If I rotate this omega 1 by 2 pi, I should reach back this point. However, you must understand, if I rotate on the omega plane by 2 pi, on the z plane, I will have to rotate by 4 pi. So I have covered the z plane twice when I cover the omega plane once, and therefore 2 sheets, 2 branches. And another reason that we have branches and sheets is you cannot find out the differential for a multiple valued function. It is just not possible. You have to make the function single valued because you have to find out the differential of the function at a point. If you have multiple points, how can you take out the differential? You understand this thing. I have a curve like this, I have another curve like this, another curve like this, and I have multiple points. I will take out the differential at this point. I will take out the differential at this point. I will take out the differential at this point. So I need to separate out into different sheets. So what I'll do is I'll just place it on one sheet. I'll place this one on another sheet. I will make another sheet. I will combine all these sheets and I'll make a Riemann surface. This is what I will do. Any other question?
Yeah, ma'am, one question is from Jahang. Can we take the region 2b between 0 to 2 pi for z and find log of z1, z2 in the principal value?
Yeah, I did that. I did that. But it depends on the log that you're taking.
It's natural log.
So natural log means you're talking of small ARGZ, and if you're talking of capital ln, then the idea changes. I think I should simply go over to the pictures that I have drawn and should be here. Here it is. So I have taken this example for 0 to 2 pi only. So I've already taken that.
Okay. And ma'am, one request is there to share the reading page again.
Which page?
The references page, ma'am, from where they can read.
Oh, okay. Yeah. Okay. Maybe I can actually tell them what is where. That's a good idea.
Yeah.
So maybe go here. So for the students, the MR Spiegel theory and problems of complex variables that you see is a Sham series. You have solved problems here. So if you want to just simply solve problems and look at some physical questions which are towards the end in the miscellaneous or supplementary parts, please go over to Spiegel. Brown and Churchill is a beautiful book which actually tells you the concepts of the capital ARGZ, the best book I have found here, and also Focus, which I'm going to tell you. Kresik is also a fundamental book. Spiegel, again, advanced calculus will have different problems. But if you're looking for the physical insights, like if you're looking for equations to fluids, you study of fluids, or you're trying to look up for some applied mathematics. See, the idea of teaching complex in a very simplified manner today was that you should understand you're trying to write an analytic function, you're trying to get the derivatives, and you're trying to write series which are important in applied mathematics and chaos theory. So when you are studying from Afkin, you will get an insight into physical problems. Similarly, Greenberg is such a book. Bauss is a very fundamental book, and very politely it is going to tell you things. Pipes and Havel is also a book which you should study once you have established your basics. Focus is going to help you for all the geometrical understandings that you get. And Sokolnikov and Rederfer is a very old book, but it has very good physics problems which you can go over to. So these are the books that I have here for you. And there are many more, but I think to start, it will be good.
Now there are
Varsha,
praises, ma'am, not the
Varsha,
question. Yes, ma'am.
I would like to read out the last comment by
Yeah.
Arya
Yeah,
Gauri.
please.
Yeah.
Yeah, please.
So Dr. Savinder, listen to this.
Yes.
Unlike the usual mathematics classes, which is only formulae and problems, this was really an awesome class. This was more like visualizing mathematics with physical concepts. Thank you so much for all the efforts. And Kirtana writes, ma'am, it was really helpful so that I could really clearly understand many concepts. Thank you so much. And there are many others writing thank you to you. So as I
Thank you.
said, so as
It
I
is my
shared with you,
pleasure, and thanks to you because you gave me the
I
opportunity
told
of
you,
this platform. I'm so
I am lucky.
thankful to
I
you.
always choose good speakers. so,
Thank you so much.
thank you so much, and definitely we'll have another lecture by you someday, isn't it? We'll be having another lecture by you someday. Would you plan to take another lecture by? Okay, voice is breaking. Voice is breaking. Voice is breaking.
Saturday again, double series 8 on Saturday. Friday I'm picking up maybe I can break up Saturday. So these will be the topics, and if students can read and come, it will be really interesting to answer their
Okay.
questions.
So I request you to pass on this page to me. I will post it to them. They are connected to us, and they will read in advance before your class. So thank you so much, Dr. Savinder. It was really a pleasure. It's after
Thank you so
ages
much.
that mathematics, as I said, is taught so sweetly. So thank you so much. Generally, it goes generally in
Thank
a
you
very,
so
very,
much.
very matter of fact manner. So it was really a very nice division. Thank you so much. And it was indeed a pleasure. So I hope all the attendees have filled the attendance, that link that was floated onto the chat box. And with this, we can end the session today. So Ms. Varsha, Dr. Savinder, I, along with my organizing team, thank you very much again. And if you give us the permission, we would like to stop
Thanks
the
to you.
meeting
Yeah,
formally.
please.
Yeah,
Yes,
thank
yes,
you so
please.
much, ma'am. Especially
Thank
the
you so much.
contour integration diagrams where you express the lines is very well and also help me to understand it better. So thank you so much, ma'am.
Yes, this series is not just for
Thank you
students,
so
it's
much.
for
Yeah,
teachers also.
thank you, ma'am.
Okay, Ms.